Good morning, everybody. Just waiting for a few more to join us here. Hopefully, you had a great evening and morning, and we'll get started here in just a moment. Yeah, we're just waiting a couple minutes here for. I had a good portion of the class still missing, so I figured we'd wait just a minute or two. Go ahead and use that green check. Let me know you can hear me okay and you're ready to go this morning. Great. Actually, what we're going to do, let me stop this here. Let's go ahead and start up this morning with just a little bit of a kind of a review checkpoint kind of thing. See how everybody's doing. Let me go ahead and pull up the link for that. Give me just 1 second. So let's go ahead and do this first checkpoint first thing this morning here. Let me give you the link actually in the chat as well, just so it's there and easier to access. We're going to do 2 checkpoints this morning. We're going to start with this one, then we'll have a little talk, and then we'll have one more. We're not going to do them directly back to back, but kind of fairly close. After we talk about the model training discussion, we'll have a checkpoint in there. All right. So there's the chat. In the chat, there's the link to the to this kind of checkpoint. This kind of just gets you, kind of assessed what you've retained from what we've discussed, and gives us a chance to kind of discuss some of these things if maybe they're not clear enough, right? So go ahead and take a few minutes to do this. We're going to do maybe 10 minutes max, okay? When you are done with this, go ahead and use that green check. I'm going to clear it all right now. go ahead and use that green check to let me know you're done. So if everybody's done sooner, we'll just move on sooner. Okay. So go ahead and go through this. It's just a handful of questions. I think 7 or 8 questions or something like that. And it should go fairly quick for you. Less than 10 minutes usually for this. So go ahead and get that done. Let me know when you are done by using that green yes check. All right, I went ahead and reposted that in the chat. I know some people, if you come in late or if you leave Zoom and come back, the chat is not there, the history. So if you missed that, I just put it in a second time for you there. And yeah, my name is Demek, D-Y-M-E-K. Again, if you're just joining us, we are working on the just kind of this checkpoint. This is just first of two checkpoints we're going to do this morning. But this just kind of see how you're doing. When you are done doing this checkpoint, go ahead and just mark you're done by using the green check, if you would, in the Zoom interface there. Maybe just another minute or two here. Um, I hope I'm pronouncing your name right, but I believe it's VJ. I got your direct message there. The results won't be exactly the same. In fact, they can be a bit different. As long as you didn't get any errors along the way, I think you'll be okay. You'll be all right. I think we'll continue to move forward. Unless you continue to see a problem, you can always go back and fix something later. But one thing I have noticed, this goes for everybody real quick. It was brought up that the results may not be the same as what's being brought up. Some of the data sets I believe have changed, and they've not updated the answers, if you will, of what to expect. So the answers are not quite the same, and so that's okay. If your I say answers like your test results and things like that, if they're very different than what's provided as an example or an expectation, it's okay. I won't I wouldn't hold your hat on that, if you will. So go ahead and just keep moving forward as long as you don't get any errors along the way, and it looks like the code that you used kind of matches and is what it should be in your projects and things. I would say just move forward. Okay, just a little note on that one. Okay, so let's talk about this checkpoint here real quick. I want to walk through the questions and answers for you. So here is I go through it real quick and just kind of answer so that we can kind of look at it question by question here. Okay. So which of the following is not an example of machine learning? This one is just simply a very basic task of saying, hey, I got my barcode. Okay, that one's pretty straightforward, right? Now, supervised learning is a labeling kind of situation, right? So I want to kind of just highlight a couple of things here. Identifying birds in an image. We're trying to identify specifically a bird, right? So we need to know what a bird looks like, not just that there's a bunch of things that all kind of look similar. Okay. So that's where An unsupervised learning problem, you could group a bunch of things together and maybe you end up with birds, but they're not called birds. They're just a bunch of things that all look the same or similar. But if we want to specifically look for birds in an image, we're going to need to have something labeled to say that's a bird, right? And so just like I could talk about on day one, how a toddler learns or what have you, you can point to a bird and say that's a bird, right? But without that, if nobody ever told the toddler that that's a bird, the toddler eventually would learn on his or her own to see these things flying around in the sky and realize they're all kind of similar, but wouldn't have a name for them and wouldn't, it's the same kind of thing here, right? So we can label it a bunch of flashcards with a word bird on it, or a bounding box or something that says bird, and that would be a labeled scenario, right? So that would be supervised. This one is real estate companies basically trying to, let's see here. This whole fully connected neural networks, yada, 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 is kind of extraneous information in all reality. We're saying, hey, we've got previous 10 years of home sales, and we're trying to predict the final sales price. Okay, that's the challenge that we're trying to go for here. Predicting a final sales price. So we're not trying to classify it in anything. So right off the top, you could we're not going to put it in groups. Okay, we're not trying to say it's in this range or anything like that. We're saying it is this price. Okay, so that immediately removes any of your classification problems, right? And recommender system, making a recommendation for something, that would be like, hey, you bought these products, we want to recommend that product. Again, it has nothing to do with predicting a sales price. So you're left with regression, which is exactly that. Regression is used typically for predicting a number, okay, an exact number, as opposed to some category or something, right? As far as when the pipeline actually learns from your data, it does not learn from new information when you're making predictions. It never really learns from that, okay? You had the learning process is the training process, okay? And again, if anybody here has any particular questions on any of these, maybe you got stuck or you don't agree or you want to discuss it, just let me know, okay? As far as which feature of the SageMaker you can use for pre-processing your data, I think the way this is worded is kind of weird. A notebook instance is considered a feature of the SageMaker service, but it's kind of a product of its own, right? A SageMaker notebook is very different than a SageMaker training service or SageMaker endpoint for hosting the models and things like that. But this is considered a feature. So just that's where it kind of throws you off here. And the word feature, we're not talking feature like in machine learning context, right? We're talking about feature of a service. When you're talking about a service and you say, oh, it's got these features, we're not talking about machine learning features, right? So notebook instance performs all this work, right? So you've been working with this now for a couple of days. You kind of log into these notebook instances, you do some work. That's meant to be able to do a lot of that pre-processing work. Now, that's just for initial exploration and whatnot. I do want to highlight something. This is just to kind of come up with your scripts and part of your automation. So when you're all done and we create a model, new data comes in, it's also going to have to be pre-processed. I'm not going to tell you how right now, but I can tell you can automate that pre-processing step without a notebook instance. The notebook instance is for initially doing the manual work on creating the scripts, creating the automation. But then in all reality, we're going to host that automation as well and make it so that I can send dirty data right to the machine learning service and get my results cleanly, okay? So it can do, the SageMaker has the capability of doing the pre-processing for you, or you could choose to do some sort of ETL process or something outside of SageMaker if you wanted to use like Spark or something like that and perform some sort of transformation on your data there. Then it's all cleaned up and submitted to SageMaker in an already pre-processed fashion, right? In fact, SageMaker notebooks have the ability to hook into Spark. There's a whole additional thing we don't even talk about in this class. There's lots of features we don't even touch on in here. It's just too much to do all in one class. but there is Spark integrations and things like that. So if you want to use Hadoop environments, so Spark environments, things like that, in conjunction with your notebooks, you could absolutely do that if you wanted to. But like I said, SageMaker actually has pre-processing automation built into it. The notebook instance is more for that kind of IDE creation kind of phase. But once you've created, you can then deploy those pre-processing actions as an automated step. Okay. As far as installing libraries and importing data and things like that on a notebook instance, you really don't want to go log into a notebook instance and then do a bunch of manual installations. You can, from right in within Jupyter. In fact, you can do pip installs and things like that. You can also go to the console of the notebook OS. I didn't point this out yesterday, but when you're in your Jupyter notebook, there's a spot in the upper right-hand corner on the main page. I believe it's upper right-hand corner if my memory serves me right. And there's a console option. You can go ahead and drop to the console, and you can actually get to the OS if you have permissions and do commands there if you want to install stuff. The problem with doing it all manually like that is if I want to recreate my notebook instance, I have to know all the manual steps and I have to do them manually. So you're better off putting them in a configuration, an automation script, basically, that every single time we create this notebook instance, it's identical every time. That way we can create it, we can destroy it. We don't have to keep this consistent all the time. It's a huge cost savings measure because, we don't need to leave these notebook instances running all the time. Only when we need to use them do they need to be running. Otherwise, we can destroy them and we can recreate them whenever we need to. And that's not a problem. Okay. And then that way it's identical every single time it gets created. All right. Okay, now this one usually throws people off. Does anybody I'm actually going to lower all of the green checks there, clear all that feedback. Okay, did anybody struggle with this one? I almost always get people that struggle with this one. Anybody that doesn't even or didn't agree with the answer, even didn't quite understand what we were going for here. Okay, yeah, and there's almost always a few, right? So at least a third of you, it looks like, and I expect that. So let me walk through this one. This is the one I feel like I have to really kind of dive into a bit. So here's the thing. I want to highlight a few things. We're talking about 30 different growers of these coffee beans in 3 different countries. Do you think we could just create some random flavor title and hope that when a grower tells us, oh, this coffee bean has chocolate notes, so put it in the chocolate category and just drop it in there? If we did that, do you think that we would have, in our chocolate category, that we would probably have way different flavor profiles, and maybe some didn't even taste like chocolate, to some people? So that doesn't really work, because you would just have like an arbitrary category that you're just shoving stuff into. So we need to somehow figure out how to group these things together. And in all reality, you probably couldn't just say chocolate, right? If anybody's ever, if you're a coffee drinker or wine or any of these kind of things, there's always these different tasting notes, right? So it's not like it's just tastes like chocolate. It's usually going to have many different flavors within it. Some people might taste chocolate. Some people might taste some kind of berry or something, or vanilla, or, who knows? I mean, it varies from taste bud to taste bud. So instead of trying to force things into particular categories, or what we would call classes, we would rather have this actually be an unsupervised learning problem and actually just group similar beans together. We don't have to have a name for it, right? This goes back to that labeled versus unlabeled kind of scenario. If we want to call something a bird, we need to tell it it's a bird, right? But if we want to group a bunch of things together that have similar flavor profiles, we don't really have a name for that necessarily. We kind of want the system to group for us automatically. Now, I always get people to come back and say, this is subject to the baristas that rate it. And I 100% agree it is. Almost all data is subject to people at some point. This is actually one of the places bias comes from, is your data source, right? You could argue this about almost any and all data that you work with. All right. Human beings are the majority of your inputs. All right. It's something like there's many zettabytes of information out on the internet, the world now. And there's been a bunch of Gartner stats on this and stuff that I've read in recent years. And 95% of that data is unstructured. And breaking that down even farther, over 70 to 80% of that 95% is human generated, right? So point is, the bulk of our data that exists on the planet is human generated. Okay. But that's why you also want to make sure that you probably have enough people doing this. If you just had one person rating them, that probably wouldn't make sense. So instead, we have these 20 different dimensions, and a human eye may look at this and not really identify any kind of pattern, if you will, there, right? It'd be really difficult because you have all these different dimensions, and you're like, I don't know how to put these into a group. And remember that thing we talked about on the first day was, sometimes we have scenarios where one of the reasons we use machine learning is because we don't know how to solve the problem, right? You could have these 20 different dimensions, and if you have a bunch of different tasting baristas, and each one of them, let's say you got a single bean that they're tasting, and you have 50 people rating it, you might have 50 different combinations of dimensions. In fact, you probably will, right? No two people will probably have the same results, right? And so it's going to make it very difficult for a human being to identify any kind of commonality here between these things. And so when you run it through an unsupervised problem, this is actually what's really amazing about unsupervised grouping or clustering kind of mechanisms, is that now what you do is, again, you take an algorithm and ultimately you're applying that algorithm to the entire row of information, all 20 different dimensions. This algorithm is being applied, and then the weights are being adjusted and things are happening, and it's looking for patterns. And ultimately things are being grouped together to see that, wow, when we change the weights on these different things, these certain groupings of beans actually tend to kind of hold the same similar or same results, right? And so it starts to emerge some sort of grouping that comes out of the profile at that point. Okay. So imagine 20 different dimensions. If you think of it in terms of, like, we go back to that bird example. If we didn't want to identify a bird, but we wanted to identify animals with certain common traits or something, right? You could have 20 different traits. Spots, no spots, feathers, no feathers, those types of things, 20 different dimensions, and you could kind of group animals together, right? Same kind of thing with beans. Okay. So in this case, it's just flavors, but, and the different dimensions, by the way, of the flavors could be, don't forget, we're not going to just say, oh, it tastes like chocolate. It's going to be different tasting notes, but you're also going to have like bitterness, sweetness, spiciness, strength of the flavor, boldness, that kind of stuff, right? So all sorts of different dimensions you could go off of, not just that it tastes like chocolate. Okay. And if anybody, here is a coffee drinker, you go into a coffee shop, it's like this, right? You go in and you're buying some kind of bean, and they've got, 100 different types. And, they have some that have certain flavor profiles, but it'll say bold on it, or it'll say robust or some kind of word like that, because it's a very, or it'll be dark, very, very strong flavor profiles. And you got others that are very light, and they may taste similar, but one's much more robust than another. And so they're in very different categories, right? Because of the strength of the coffee as well, right? So that's kind of the big picture. So if we look at some of the different answers here, categorizing the beans in one of two categories indicating the two main flavors represented, that's not, if we have 30 different growers in 3 different countries, we're going to have 2 categories full of coffee beans that really have no similarities, right? I mean, they're going to be so far different. So we want to kind of find what groups emerge, right? What categories emerge from this. And so then this other one here, categorize different types of beans into multiple categories, indicating different types of flavors. And again, you would have to come up with the categories, right? So do you think you could, as in a good business sense, come up with the exact proper categories that these 30 different growers are going to produce, right? And that's the problem with business in past years, is without machine learning, that's exactly what a business would do, is they would make up their own categories, and it would be a forced thing, and you're going to have some things that you're like, I think it could belong to all 5 categories. We have 5 categories. I think this could go into all 5 of them. Which one do we put it in? And then you just have to grab one, right? And that's not going to be good either. So by letting the data tell us what category or what group it should be a part of, right? When I say category, I shouldn't use that, because it's not a class at that point. It's just a group of data points that say, hey, these are the most common, right? These are the most common with one another, okay? It doesn't mean predefined categories. Yeah, but that's what, when it says categorize different types of beans into multiple categories. Okay, great question. So maybe this is some of the misunderstanding here. Is an unsupervised learning problem does not categorize. Okay, it does not categorize. It groups. And I know those may seem like similar words, but a category is a class. Okay. And so we're saying categorizes different beans into multiple categories, indicating different flavor types. So first off, a couple things wrong with that statement. Just flavors are not the only dimension. We have 20 different dimensions. Flavor is probably just 1 or 2 of those dimensions, or maybe 5, let's say. There's 15 other dimensions we're not even considering there. So that's problem number 1. Problem number 2, if it says into multiple categories, what are those categories? What should they be? So if we're saying categorize them into those categories, it's implying that those categories already exist. We don't know what those categories should be, right? And so if you don't know what those categories should be, we need to let the system do the grouping, okay? And so that's where this third one here is the closest answer, in that sense of, anytime you see the word categorize, typically we're thinking classes, because that implies that you have categories, right? That you have groups, that you already have groups defined, right? So if I tell you to categorize something, you're going to say, what are the categories? Right? I mean, just think about that frame of mind, okay? Taking the semantics away just a little bit. If I tell you to categorize things, you're probably going to need to know, I'm going to say, put these into some categories. You're going to need to first say, here are the categories, aren't you? Right? You can't just categorize as you go. You would have to identify your categories so you could start putting things into them, right? So instead of doing that, we can just kind of start to group and move things around and kind of start to say, okay, these things look like they're similar over here. These things look like they're similar over there, and kind of start to group them as we go, right? So grouping is different than categorizing in that sense of not having a predefined category, okay? Yeah, exactly. And it's just a way of thinking. But again, even outside of the ML space, if you were to categorize something, no matter what it is, right, you need to have your categories to categorize them, right? So without categories, you got nothing to put them in. So you're going to have to first say, okay, well, I think these are the 5 categories we need, right? Wouldn't that be accurate to assume, right? I know what they say about assumptions, but the idea there is that you would have to come up with those categories, and the big question is, are they right? But like I said, there's actually 2 problems with this second answer, and one is the categorization problem. The second one is flavors sticks out here. Okay, so even if you didn't clue into the categorize kind of thing, different types of flavors. It says 20 different dimensions. It doesn't say 20 different flavors. And this is what's very important to understand is those dimensions are attributes about the coffee beans. Maybe even color of the coffee bean may come into play, visual color when it's roasted, right? And age of the bean, flavor of the bean, bitterness of the bean, sweetness of the bean. You get the idea. And so flavor does not meet the requirements. All right. There's a lot more to flavor than just flavor. Right. Okay. And then the very last one, predict the numerical output for different types of beans based on past ratings of similar beans. You could come up with something complex here that might work to some degree, where you kind of give it like a value of some sort. But you're going to have values all over the place. And so the question is, again, are you trying to then shove those values into a certain category? Basically, you're trying to recreate what unsupervised learning does for you at that point, right? What you would do is produce some sort of numerical output, not just 1 through 10, because if it's 1 through 10, you're just categorizing at that point. You're creating a category, But if you're just saying, hey, create some numerical output, some algorithm, some mathematical equation, and you got 30 different growers and tons of different beans coming from those growers, right? Keep in mind, it's probably more than 30 different beans, right? They come from 30 different growers, which means each grower probably has, many different flavors and many different beans. You probably got hundreds of different flavors here, right? Total, if each grower has, 10, right? I mean, you start doing the math, you start realizing that's a big number, right? So we're just going to have a calculation or some sort of mathematical equation on that last number where they're all going to have a different number. What does that do for us? Right? Well, we're then going to try to have to interpret that number and try and group them after the fact, which at that point, why not just use, something that's even smarter than that, than us, right? And that's where grouping similar beans together based on ratings by baristas really just kind of makes the most sense there. Right. Is that making sense? Is there anybody that disagrees? I mean, feel free, to jump in and say, well, here's how I think of it. I have no problem with, good dialogue there and kind of discuss that through. But that's healthy, right? So if anybody else has any other, thoughts or feedback on that, but the word categorize kind of stands out to being classes. Okay. And different types of flavors is not robust enough of a solution. Okay. There's kind of two problems with the second answer there. And then the first one, 2 categories absolutely wouldn't suffice. Right. So, and then this last one, numerical, output just gives us a number, but what do we do with that number and how does that help us? Right. So it kind of leaves us with the third answer. Are we good? We're good. Yeah. I don't know the feedback on that. So I'm guessing silence means we're good to go. All right. Oh, great question, Jeffrey. No, not at all. SageMaker is just an API, and I can run SageMaker commands. I can use the SageMaker APIs and SDKs directly from my laptop if I want. I could run them from an application running anywhere in the world. Okay, it's just like all other AWS APIs and SDKs. With the proper authentication and authorization, which would be like keys and permissions, you can do this from anywhere in the world. Yeah, it's just one of the reasons why we like SageMaker notebooks, just for experimentation. I do also want to point out, just for experimentation, the notebook, that's all it's for. Okay, it's not for launching the training job. Okay, we're just launching the training job as an experimentation process so that we could launch a bunch of different ones, right? We launch one, we play with it, look at the results, then do another training job, play with it, look at the results, launch another training job, look at it, play with the results. But when we've developed our pipeline, then we don't want to do that. And we don't even want to use SageMaker notebooks for training jobs on an ongoing basis. Because once we've established our scripts and automation and all of that, I want this to be a fully automated pipeline where we do the data pre-processing automatically, and we automatically kick off new training jobs if we need to perform new training jobs, right, against the same data. So this is just an experimentation tool, all right? SageMaker notebooks will not typically be part of my production process. and they are just a way to do it centralized in AWS so that we're not moving data back and forth in and out of AWS consistently, which would be more expensive and slower, right? So one of the reasons why we use a SageMaker notebook is because it's in AWS, meaning the data doesn't have to go all over the place. It can just point right to S3, and the notebook exists in AWS as well. So it's talking on the back end core network, right? It's using the backbone and all that stuff. And it's going to be very, very fast. And of course, with the SageMaker notebook, we can just specify the resources we need for it right now to do the work we're doing. Unlike your laptop or something like that, which would be much more fixed. I would not recommend you do this work from your laptop because of all of that, right? It's going to be more expensive, most likely, to do it from your laptop because, and time consuming. It's going to take a lot more time because as you're doing data pre-processing with your notebook, you have to pull the data in, right? The data exists on, let's say, S3. You're going to have to pull that data in and work with it. And then when you perform a training job, what do? Now you're going to have to send the data back after you've pre-processed it back to S3, which means, again, over your internet connections and all of that. That's very slow in comparison, right? We've got massive, massive networks inside of AWS, but as soon as you go outside of AWS, you're dealing with internet connectivity or private connectivity you might have, which is going to be substantially slower. Okay. And then the ability to just choose your resources on a SageMaker notebook is also critical, right? If I'm doing something that requires a lot of resources, I can spin up a SageMaker notebook that has hundreds of CPUs and terabytes of RAM if I needed it for a short while I'm doing some work, right? I could do that. Now, I'm not going to do training jobs on the notebook, but if I'm going to trigger the training jobs from the notebook, that means the data has to exist somewhere, which means the data I pre-processed on my notebook, I have to save back to S3, all that. So you can start to see why it makes a lot of sense to use the SageMaker notebook to do it. But all we're doing with the notebook is it's just a client, and it's just running API calls that are accessible from anywhere in the world. All right. Yeah, very good question. All right, so that's it. All right, let's move along. Let's talk about training, in fact, on that note. So model training. So we're kind of starting to progress through this pipeline a bit more. Business problem, business formulation. We spent a long time on the first day on that one. Yesterday, we were kind of mainly focused on data collection and data pre-processing and visualization, right? We kind of saw the need for a lot of that and how we work with that data, blanks, anomalies, our outliers and things like that. Keeping outliers that are rich, that can add richness to our data, that are real, would be a good idea, but that are natural outliers. But if they're false, we want to do something with those, right? And then the ones that are real, even at times, it may make sense just to replace it with a mean or median or something like that. But just realize you are taking richness out of your data that could absolutely be valid and valuable to you, right? So we'll talk more about scaling and things like that later. We're going to get to that, okay? So model training. So we're going to get into algorithms, formatting our data, and all this good stuff here. Let me just one moment here. I'm going to check on something. Okay, I kicked off a training job a little bit ago. I'm going to do a demo here for you in just a moment. I just want to make sure the training job was good. All right, so let's talk about algorithms. All right, so here's the thing. Remember, the training process is running your data through algorithms. Again, it's not just looking for patterns in the data in the traditional sense of, oh, look, every time there's fraud, it's over a certain dollar value. That's not, that would be a classical programming approach, not a machine learning problem, right? We're doing something much more advanced here where it's running an algorithm against your data with weights. Then the weights are not part of the data, right? The weights are separate. The weights are an extra variable as part of the algorithm, and then it runs through the data, and then it changes the weight and runs through it again, and changes the weight and does it again, changes the weight and does it again. And that's the kind of a general concept of the way most of the algorithms work. And so you're not running through your data one time, you're running through it potentially hundreds of times. And we're trying to see that as you make adjustments, what patterns emerge from the outputs of the algorithm. Okay. And the algorithm is key there, right? The correct algorithm for the data that we're working with is going to be absolutely critical. Okay. So choosing that algorithm is an important step here. The main goal here, though, is we want to make sure that we have an accurate model that basically is correct as often as we need it or more. Okay. We don't want to just have it be a guessing process. Now, as I mentioned, I want to highlight this. It's not brought up in any of the slides. I already mentioned it to you at least once, maybe twice, but I'm going to say it again. Be very careful with how you measure success, in that if success is equal to the norm, did you really do anything? So as an example, if I think I've used this already, right? But with the fraud situation, right? If 5%, 1% of my real life transactions is fraud, 99% of the time it's not fraud, my model is going to need to be a lot better than 99% accurate. Think about that for just a second, right? 99% accuracy on fraud at that case. Now, it depends on how you measure accuracy. This is what we're going to get into. We're going to talk more about the measurements there. There's precision, there's accuracy, there's recall sensitivity. We're going to get into those things because those are more critical here. Because if all we're doing is caring about the percentage of times we're correct of predicting fraud or not fraud, then 99% would be, without a machine learning model, we could achieve that by just simply saying it's not fraud. Okay. And I know I've said this. I really want to hammer this in because some people mistakenly, no matter how many times I say it, it's inevitable. Somebody goes and creates a model and they're like, oh, I'm using just regular accuracy as a measurement. Okay. Now, again, that's where using the right measurement is important. But if all I'm doing is measuring accuracy and I say, look, I was correct 99% of the time, that's pretty good, right? Except for the fact that you were wrong every single time there was actually fraud. Okay. So keep that in mind. The measurement here is something we're going to get to a little bit later, but measuring success right here is you can measure it incorrectly, and you can incorrectly say you're successful when you're not at all. Okay. And then choosing the right algorithm is critical. Okay. So as an example, forecasting some value would be very different than threat detection, that, hey, this is a threat, yes or no. Okay. Completely different algorithms are going to be used for this. Okay. So we have a handful of slides here that kind of help you map this out. These are really helpful to kind of help you show which algorithms fall under certain types of machine learning problems. Okay. So our most basic supervised learning algorithms, we've got classification problems, regression problems, and recommendations engines. These are all supervised learnings. This gives you a handful of algorithms down here at the bottom that meet these needs. Okay. And you can kind of map them out and see, where it makes sense. Okay. And again, I want to point out, let me just, I'm going to kind of take a pivot here for just a second here. Let's see. Hopefully this goes well, because I wasn't prepared for this. But I think this is a really important thing. I've gotten a feeling in the classes. I've gotten certain questions from people privately and publicly that I need to kind of maybe clarify this. Give me just a second here. So I'm just going to pull up a spreadsheet here. Okay. So let's just say, whoops. I've got all these values. I'm just going to kind of fill them in here as quickly as I can. I'm just kind of popping values in here. Okay. All right. Okay. Just making stuff up. Okay. Oops. Don't want any letters in there. Okay. And then I have some number as an answer. Okay. So I've got, this is why you don't want to look at data first. I'm going to show you what I mean here. So feature 1, feature 2, answer. Okay. And so let's just say our data looks something like this. Okay. And you might think, hey, this is labeled data. Well, not necessarily. Okay. Because we have an answer. And I'm just saying we've got this, maybe we have some sort of thing in our system. We've got this column that looks like that. What kind of problem are we going to solve? Some people might look at this and go, well, this is a supervised problem. We've got the answers here. We can just strip the answer. Well, no, that's just a calculation. That's just something that happens to be in our data. If we're trying to predict fraud, in all reality, this has nothing to do with that, because what we're going to do is we're going to create a completely new problem with our machine learning. And we're going to say, no, we're predicting true or false. We're predicting fraud, not fraud. Okay. And so label would be 0, 0, 0. And we would add this, perhaps. Maybe we need to go dig this up, right? And so we've got true or false, right? But our original data had nothing to do with that. Okay, our original data was just some numbers, and some people might go, well, it's a bunch of numbers, so therefore it's a regression problem, or it's a bunch of numbers, it's a supervised problem. We already have an answer here. That has nothing to do with what we're trying to forecast. Okay, so we got all these numbers. It's not a regression problem just because there's a bunch of numbers there. That's not what we're trying to do. This is why we don't look at our data first. This is why we go, no, here's the business problem we're trying to solve. We want to know if it's fraud or not. Now, oh, look, we've got this data, and we want to predict if it's fraud or not. Well, maybe we have to combine data from different data sources to identify, oh, this transaction was fraud, okay, and label it, But the data itself doesn't make it a regression problem, okay? Just because we've got a bunch of numbers we're working with. That's not a regression problem. It's what are we trying to forecast? What are we trying to predict? What are we trying to infer? Okay. Very, very important to kind of grasp this concept. And I hope I didn't just confuse some people. And I mean, it's kind of vague, but I didn't go into all the details about what those numbers would be. I kind of made some stuff up on the fly. But my point is, just because you see a bunch of numbers doesn't mean it's a regression problem. Okay. What are you solving? What are you solving for? Okay. Should be actually fairly easy to do to identify that, right? Because as a business, we say we need to know this information. We need to know if it's fraud or not. Okay, you know what? As a machine learning problem, that is a binary classification supervised learning problem. Well, therefore, let's maybe consider using linear learner or XGBoost. You see how we did that? I don't have to look at the data to do that. Okay. Then we go look at the data and we say, okay, it's sufficient for predicting what we're trying to predict. It's got the right information in it, right? Okay. Unsupervised learning. We've got things like clustering. We've been kind of mentioned that a bunch. Clustering is that grouping kind of concept. We've got topic modeling, embeddings, anomaly detection, dimensionality reduction, PCA. That was actually asked, I think, on the first day about PCA. We don't really get into this, but this is just an algorithm of unsupervised learning. Okay, so you could apply this to maybe even reduce your dimensions. So this goes back to that whole idea of how many features you have and feature correlation and all of that. PCA can help you reduce those dimensions, help you reduce the features down. It can be a way where you apply machine learning to your data that you're ultimately going to do a different model against. Interestingly enough, this is why I said a lot of times multiple models may come into play. I may apply a model against my data to help me identify the features that I'm going to use in a model to predict fraud. Okay, just give you an idea, and that would be a totally different. So I'd use PCA and linear learner, right? PCA would be for model 1, and then linear learner would be the one that actually produces the binary classification, right? So that's where we would create multiple models to do different tasks. Okay. Okay, can anomaly detection? That's a great question, Odette. Can it? Maybe, maybe. It's actually a little bit misleading a lot of times. Is an anomaly fraud? Think about this on how people use their finances, depending on the, I mentioned this one, I think on the first day. I've got credit cards that I don't use regularly. I've got some credit cards that just kind of sit, and I don't even carry them in my wallet. I just kind of, they're locked up. And then if I want to make a big purchase, maybe that's where I do my big purchase, because I don't like to carry balances and stuff, and I have credit cards I use every day, but I pay them off every month. And so, but their interest rates are higher. So if I want to get, pay something off in a 3-month period or something, I'll go use a different card for that. And so, so is that an anomaly? If I haven't used my card for 3 months and then suddenly I go make a $2,000 purchase on it, is that an anomaly? Yeah, it is. Right. It's out of the norm of my behavior is that I don't buy stuff first off. So as soon as I do buy anything, it could be an anomaly. Right. But it's hard to say. I mean, if I use the card enough that way, it could create some sort of baseline. Right. But if I use the card like 3 times in the last 3 years, it's going to be really hard for anomaly detection to identify that. So, it's going to be really, really hard to create a pattern, you see. So, yeah. So, Jeffrey, then there's more, by the way. We're not done. We're just showing you categories for these different algorithms for these different categories. There are, I don't know if we're showing you all the algorithms here or not. I'll show you all of the algorithms though. There's like 17 or 18 of them built in. Now those are built in, but you can use SageMaker for any and all algorithms that exist on the planet. You could even write your own if you wanted to. So SageMaker is extremely flexible in that sense. But wonderful question, Jeffrey, on that front. Okay. All right. So these are for unsupervised learning. And then we're just kind of showing you how you choose these. For text, we've got a bunch of others, right? So text classification, word to vector, we got machine translation, topic modeling, speech as well. And then we've also got images and video and time series. You see there's a lot here, right? So these are just, I mean, we're not going to cover 99% of these, right? We're not even really going to cover algorithms per se in this class. Okay, specific algorithm selection kind of depends on the problem you're dealing with. And that's I mean, we could spend a really long time on just one of these algorithms, right? So we don't really focus on the algorithms in this class, and the certification doesn't really focus too much on the algorithms either. Just more about the usage of the algorithms, like, selection, understanding that certain algorithms belong to certain problem types. It may not be a bad idea to kind of just have a general idea of some of the kind of core algorithms, if you will, like your classification. If I come back here, understanding that, these on the supervised learning may not be a bad idea to kind of know about XGBoost and linear learner just a little bit. Those kind of come up a bit. KNN, just kind of understanding. These may be mentioned on an exam, but they don't expect you to know the details of it. But it may be in the context of a question. They may include like just for robustness of the question, if you will. If that's the word, robustness. If they just want to kind of add depth to the question, they may include something like KNN or XGBoost in the question. It doesn't mean that they're asking you anything really about it, but it may add some context, and knowing what they're talking about is helpful, but they're not going to typically go into crazy depth of every one of these. Okay. So, but lots of different algorithms to choose from. Now, while we're on it, let me just kind of show you the documentation on this. Okay, you just do a search for algorithms, SageMaker algorithms, right? That's an ad. So I'm going to go down to the first organic hit right there, built-in algorithms. And they give you some great resources here. So first off, over here on the left, all the different algorithms that are included, that are built in, are right here. This will handle probably 95% or more of the machine learning problems you'll encounter. Okay, these are very common industry known algorithms that are used for the majority of problems that are out there. Now, are there other algorithms? Of course, there are hundreds, if not thousands, of algorithms you could choose from out there, and you can use them in SageMaker. But these are the built-in already there. Now, if you remember the way we talked about the architecture of SageMaker, all these is containers sitting on the repository on ECR, Elastic Container Registry or repository. That is an Amazon-hosted repo for Docker images. And so these are all in there. If you want to take one of these and modify them for your own liking, you could take the container and enhance it or change it with your own scripts. You can also go download your own algorithms or upload your own algorithms, however you want to look at that. Download them somewhere else and upload them into basically put them in a Docker image and go put them on ECR and use those. There's also stuff from the marketplace that you can do all kinds of stuff. So, but these are the built-in. Okay. As far as if these over here on the left, if I go into one of these, it's just going to give me a deeper knowledge of that algorithm. So it kind of breaks down each algorithm. Okay. So how it works, hyperparameters, we'll talk about those later in the class, model tuning, data formats. And it kind of talks about, that one. But back on the choose an algorithm, the first page, actually the first page I landed on was this one, use built-in algorithms. This right here is kind of a helpful page. You'll notice here, it talks about, again, supervised learning. So that category, right? This is kind of like a chart version of that diagram we just saw, right? Supervised learning, problem types, right? And then these different problem types and the data input format and the different algorithms that meet that need, okay? And then unsupervised, same thing, okay? Textual analysis, image processing, okay? So this helps you kind of break that down. It's a lot of the same stuff we just saw in a more visual fashion, okay? So if you want, I'll just give you this link just so you can grab it if you'd like, just so you can do some further, if anybody's interested in needing or needs that for anything, okay? Okay, so those are algorithms. You choose the right algorithm for the problem at hand. Keeping in mind, it's not about the data itself. Just because you're dealing with a bunch of numbers doesn't mean it's regression. It's only a regression problem if you are predicting a number, okay? It's a classification problem if you are trying to predict a category, right? Or a class, right? And then of course you have binary classification or multi-class classification. It's an unsupervised problem if you don't have labels already and you just want to group things together in as like things, right? So that's kind of, to understand that, then that's going to help you select your algorithm. And you should really kind of do almost all of that before you really start diving into your data a whole lot, right? And then you look at your data, and again, is it sufficient? Is it correct data for what you're trying to do? Is it going to work? Okay. Then formatting your data. The most commonly supported built-in algorithms are going to support CSVs and record IO protobuf. Okay. These are kind of the two primary ones that the built-in algorithms in SageMaker support. If you bring in your own algorithms or you do something from the marketplace, it's possible they may have their own specifications depending on the algorithm, but most of your algorithms are going to support one of these two. Okay. CSVs, pretty straightforward, or record IO protobuf is actually it's actually a binary file. We'll talk more about that in a second here. So if we're using CSVs, a couple of things we want to do as inputs. So we're performing a training job. We're gonna use this data to train. If we have labels, assuming we're doing a supervised problem here, we're gonna have our labels moved to the left. Very, very commonly, they'll be on the far right of a CSV. Okay, so a lot of times your CSVs might start looking like this, over here on this side, and your label, a lot of times people like to put it at the end, and that's normal. That's just kind of common practice. But when you go to actually run it through the system for training, the label needs to be on the left. Okay, and this is not really a SageMaker thing. This is just an algorithm thing. Okay. And these are industry standard algorithms. So labels on the left. Also, you notice we strip off the header row as well. Okay. As far as record IO protobuf formatting goes, it'll automatically perform some transformations against this. SageMaker is deeply integrated with record IO protobuf, and it will pretty much do everything for you. So SageMaker will handle those transformations on the data as it needs. If you're using Python, just use those built-in transformations. If you're using other languages, you may have to do some work. So Python is a little bit more robust here for this purpose because you don't have to do anything. If you're using other languages other than Python, then you're going to need to go to this this documentation to see what you're going to have to do with that file and make sure that the language that you're using kind of takes care of that the work there. Okay, so SageMaker will just do it for you if you're using Python. Okay, Okay, now splitting the data. Let's first talk a little bit more about this. We've briefly talked about this one before, right? We have our overall data source. So this is, our 1,000 records that we've got to work with, let's say. I'm just throwing a number out there. It could be 1,000, it could be 10, it could be 1,000,000, whatever we're training off of. So this is our whole data set. We don't want to use the whole data set to train with. Okay, just to recap, we've talked about this a few times. Again, just kind of hitting it home, saying it over and over again is going to help you retain it. So we're going to split it up, and this should be about 80% of my data. So if I've got 1,000 records, I'm going to take 800 of them and train off of them. I'm going to take another 10%. And this says evaluation, but in all reality, we don't use that word evaluation anywhere else. It's usually validation. I don't even know if that's a typo or not. It should be validation. Okay. And then that's going to be 10% approximately. So, you can play with these splits, but most of the time 80, 10, 10 is a pretty good split up. So 80%, so 800 rows would be for training. We take 100 rows and use that for validation. Now, just to recap again, what is validation? Those right there are used during the training process. So you train, and let's say, again, I've got 800 rows for training, 100 rows for validation. Maybe it goes through, some training process, and then it uses the validation data to make a prediction. So it makes a prediction inside of itself while it's training. It makes a prediction and against the validation data, but the validation data knows the answer. And so it makes a prediction to see if that prediction matches the validation data during the training process. And it helps it adjust, weights and things as the algorithm is going through those changes, as we talked about. It does a calculation, and then it makes a change to the weight, does another calculation, makes a change to the weight. So it helps it understand its error rate. And we'll talk more about that error rate a little later on. But ultimately, is it getting more correct or less correct? Okay. And that's kind of what it's trying to identify during the training process. Then once the model is totally produced, we can then run the testing data through the model that we've just produced as a final test. Okay. And then that's going to be another 100 records. Okay. In my example of 1,000 starting. Okay. So we had 1,000 records. We want 800 of them for training, 800 of them for training, 100 of them for validation, 100 of them for testing. Okay. In that example. All right. So we want to split the data because, again, if we trained you on exactly what we're going to test you on, it doesn't mean you learned anything. It just means that you memorized the test, right? So again, I already gave you this example too, but just to recap, if I just gave you the test, if we were going to give you a test on Thursday, starting Monday, I just gave you the test, and we went through the test 5 times on Monday, 5 times on Tuesday, 5 times on Wednesday, and then Thursday rolls around and we say, hey, here's the test. Hopefully you get 100%. If you don't get 100%, that would be surprising, right? Means you probably just weren't even trying, right? So it doesn't mean you learned anything. I could just get you to memorize the test pretty quickly, right? So that's the whole idea, is we don't want to train you on testing data. Testing data and training data should be kept separate, okay? If you test on 100% of your testing data first round, the first round, what do you mean by the first round? So the training process, the first round doesn't learn anything at all. Okay. Okay. So before feature engineering, no, you still don't want to do that, because you're just going to get false results. The test will say that it was 100% perfect. So I'm not talking about feature engineering at all. I'm talking about during the training process. So one model, you create one model. The process during a single model creation, it goes through your data many, many times. Okay. So it's going through it a whole bunch of times, and it's looking at that test. If it's looking at the test data the whole time, then it produces a model to the test. And then you go test it. It better get 100%, right? I'm not talking about any feature engineering whatsoever. Okay. We're not even to that point. Feature engineering would improve my model, but in that case, I'm gonna have false success, because in all reality, the model's going to get my test data 100%. So another way to word this is overfitting or being, our test would say it's 100%, but reality, I may only get 30% correct. Right. So I'm going to have a huge disparity between my test data, my tests that are run. I'm going to have a huge disparity between tests and reality. So when I go to actually put this into production, it's not going to match. Feature engineering is going to actually increase my value of my actual model to my business. Okay, it's going to actually make us better. But this is going to give us a false result of success on our tests. Reality is going to quickly show its head, though. Okay, so overfitting is when our test says looks great. Reality is we're way off. Okay, so no, we don't use test data at all to train. If you use test data to train, you will overfit, and you will basically tell yourself, yeah, we've done amazing, when you're doing terribly. Okay, your test data cannot be used for training. Now, there is a strategy I'll talk about when we talk about cross validation and some other things. There's a strategy there to be able to use your test data, but we'll get into that. But generally speaking, do not train on your test data, because your answers are going to be completely wrong. I mean, you're going to be right, but you're going to be wrong. Okay, if that makes sense. Again, I imagine if we didn't teach you anything about machine learning at all, and you knew nothing about it coming in. Okay, some of you already had knowledge. Let's imagine you're completely brand new. I just gave you a test. There's a bunch of words on the test. You don't know what they mean. A, B, C, D for each question. Okay. And I give it to you, and you get a bunch wrong, but we give you the answer. Then we give it to you again. And then we give it to you again. We give it to you again, and we give it to you again. And I'm not talking about feature engineering. I'm talking about all within the same process for one model. Okay. To create the very first model. Then we're going to say we're done after giving it to you 20 times. And then we're going to go test you on the exact same question pool, exact same order, exact same everything. You're going to get it right. And you know nothing about machine learning, right? Just because you're going to memorize, oh, that one's A and that one's B, that one's D. You know, that's what we're talking about here. So the training process, just like a learning process as a human being going through a class or something, the training process is more than one effort. The training process itself is going through that data many times, over and over and over again, before it produces a model. Then it finally produces a model, and then that model is tested. And the test is supposed to tell us how good it performs. But if the test is the exact same data we just trained it on, it's going to tell us we did really good. It's almost guaranteed to tell us we did really good at that point. Okay. So why split the data a bit more? Okay. So train, model, validate. We already talked about this much. We've hit this one pretty heavily. All right. So again, simple holdout is what we call this. This is a very basic kind of square one. Works for a lot of situations, just basic holdout. So we have our overall data set, 80% for training, 10% for validation, 10% for test. Okay. And then we call that simple holdout because we're holding out some records for the purposes of validation and for the purposes of test. Both validation and test are forms of testing, but don't forget, validation actually happens within the model. And then we test against it once the model's been generated. Okay. Let me explain cross-validation. This one before we get into it, and then I'll explain it again when we get done talking about it, because it's a very confusing topic for a lot of people, even very experienced machine learning people, and it's very difficult to explain. So I'm not going to say I'm going to explain it amazingly either. It's very hard for just about anybody to really get into. But the idea here, first off, understanding the idea here is when I have very little records to train on. Okay. Maybe I've got like 10 records. Maybe I've got 20 records. Not very many, right? Certainly not 1,000. I've only got like 10. Let's just go with the number 10 for now, just to kind of keep it simple. So I've got 10 records. If I do a simple holdout right here with 10 records, here's what's going to happen. I'm going to train on 8 records. I'm going to validate on one and test on one. This could be really problematic. What if that one record I'm testing or validating with is just a bit more anomalous? I'm just kind of using that word generally speaking, just a bit more on the edge than all of the other records, just coincidentally. Okay. I may get it wrong a lot, or I may get it right a lot if it's a really common looking record, you know? It's not going to be very good at making sure that my model is doing what it's actually supposed to be doing. It's going to make it very difficult to test correctly using only one record to test and only one record to validate. Meanwhile, training on 8 records, you could do it. It's going to do its best. Okay. Obviously, more data is the better, but you could do it. The problem is we don't know if whatever we've done with that training is actually good, because the test is so small. The results of the test may not really give us a good picture of that. Okay. More data is always better to train with, but if we don't have it, we don't have it. So does that mean we don't make a model, or do we see what we can do here? So here's the problem. We don't know if our settings for the model are good. Okay. And I'm going to talk about those settings later on. This conversation could come in a couple different places throughout the class. I actually think it's maybe a little early right now to have it, because there's some other things that we could get into around settings and things, hyperparameters and parameters. We'll get into those later. But let's kind of keep it simple for now and get the concept across. So let's say I don't know if one algorithm or another algorithm is better for this problem. The test is going to give me some slightly false results, potentially. It could give me overly promising results when I'm not doing good, or it could give me poor results when I'm actually doing really well, because of just the one record that happened to be selected. Okay. So how do I compare my settings to one another? So if I've got 2 different algorithms I'm trying to compare, or I'm trying to compare one algorithm and I have some settings that I want to specify for that algorithm, and I want to try it in 3 different possible ways, and I want to compare them, and I want to see which one performs better. What if model 1 I produce with algorithm, let's say they're all using the same algorithm for the sake of easy discussion. And in fact, let me just kind of just keep this straight. This might help. So let's just say I've got three things I want to compare. So I've got, these are all using the same algorithm, but this is going to be model 1. This is going to be model 2. And this is going to be model 3. And I'm just going to say settings for now. I'm kind of leaving it very generic because we haven't talked about those yet. But let's just say I've got very particular settings that I'm adjusting here. And so I've got setting 1 equals 5. Okay. Setting 2 equals 100. Okay. And so on. Okay. And then setting 1 equals 10. Setting 2 equals 200. And over here, setting 1 equals 0.5. Okay, 0.5. And setting 2 equals 1, something like that. Okay, very different settings from one to the next. And I don't know which settings are the ones to go with. So I'm just going to produce 3 different models and compare them and experiment, right? Sounds simple enough. But what if the record that I'm particularly testing against, like I said, is either really common or really not common or something like that? Even if I test with the same record for each one of these, the test record, okay, I'm just going to say test record goes in here, and I get a score of 95%. Okay, 95. Accuracy. Okay. We'll talk a little bit more about this in detail. Just kind of stay with me. And then test record You know, I get like 80 here, you know, and test record, I get 99. Does that mean that this one is the best, you know, Model 3? I don't know, because it's just one record. And in all reality, what if Model 1 was the better performing one in production? Right. So I need a way to be able to test on all of the data that I am training it on. But I also want to train on as much data as I can. So I want to train on all of the data too. So instead of training on 8 records of 10, I want to train on 10 of 10 if I can. But I also want to test with 10 of 10 if I can. How do I do that? And what I'm going to do is really use this just so that I can compare the success of these 3 settings, these 3 groupings of settings. Okay. So which one is actually the best one to go with is kind of what I'm trying to go for here. So so we're going to get a score from each one of these. And again, if we were just testing on one record, that score could be a little crazy. So what we're going to do is do what we call k-fold cross-validation. This is a useful strategy. Now I say strategy. This is something you can do manually, and there is a little bit of automation in SageMaker to kind of help you do some of this stuff a little simpler. But basically, this is the way we do this. Is let's say we're going to do what we call a K5. So this means we have what we call 5 folds. And the idea here is we produce model number 1 with 5 separate chunks of data. So if we were using 10 records, this would be 2 records, this would be 2 records, this would be 2 records, 2 records, and 2 records. And then we get a score. Okay, that's supposed to say score. I just scribbled. Okay, and then we do the same thing for model 2, and this is a totally different model. Okay, and in this case, we are using again the same. Each one of these is the same record set. So 2, 2, 2, 2, 2. But this time, in this second time we run through the model. By the way, all of these in this case are actually going to be the same settings. Okay, so this is where things get a little bit confusing. I'm going to do this 5 times for the first model. I'm actually creating 5 models here, but I'm going to aggregate the results to kind of understand that those settings now give me these results. Okay, and then I'm going to do this all over again for a different set of settings. And I'm going to do this all over again for a different set of settings. Okay, so each one of these is a different model. Instead of producing just 3 models like I showed you, we're actually going to create 15 models, okay, in this example with a K5. And the reason being is these produce 5 different models. Each one has a different score. So instead of just getting a score of 95, now we might get model 1 might have a score of 95, model 2 might have a score of 30. Because we're validating on a different set of records now. And so what happens is each run through, we are training on as much data as we can and validating on 2 records. The next model, we're training on 8 records and validating on 2, but a completely different set of 2. Model 3, same thing, a different set of 2. Model 4, a different set of 2, and Model 5, a different set of 2. Ultimately, we are creating 5 different models and just averaging the scores of these 5. And we do that for setting grouping 1, if that makes sense. Then we do it all over again for setting grouping 2. And we get these, we average these results, and we take those and we trust those are more accurate. Now we can say which group of settings actually is the best for our model. Then we can go produce a model using those settings, put that model into production. All right. So that way we can kind of trust our answers a bit more, because we are ultimately testing, and this says validation, but it's kind of general concept. we are ultimately testing on all of the data, and we are ultimately training on all of the data to get our scores. All right. And you can do this at kind of any scale. The whole point of doing this is comparing. It is not to produce a production model from the K-fold. The K-fold cross-validation is to evaluate. And then what we do is we go, okay, I think we've discovered our best settings. Now go produce your final model with those settings, right? And then in that case, the final model, maybe you produce it without any testing at all at that point, right? We don't need a final test because we already understand our settings. Okay, so yeah, this is a really confusing topic. So let me draw it out one more time, and maybe now that we've had that first conversation, I can draw it out again a little differently. So we have our settings here. Okay, I'm just going to say setting group 1. Okay, setting group 2, setting group 3. Okay, so same kind of thing we were looking at earlier, but here we're going to produce model 1 and a score of 95. Model 2, a score of 30, something really low. Model 3, using the same settings each time, I want to point that out. Model 3 equals 45. Model 4 equals 10. Model 5 equals 80. Okay. So because of the test, this is all about the test records. Okay. So if we had just tested on those first couple records, we would have said, wow, that's 95. And we would have thought this was really good. Okay. But look at the rest of this. This looks awful. Okay. But then we go to setting grouping 2, and using those settings, we end up with 92 as our first one, which would have made it look bad to begin with. But then we end up, keep going with different test records, and we end up 99, 98, 72 maybe thrown in there, just something, wasn't as good. And then a fifth one, like a 95. Okay. And then setting 3 is, whatever it is. Let's just say just for sake of time, but let's just say setting grouping 2 resulted in an average there. Oops, I accidentally cleared the screen, but hopefully that made sense. Setting grouping 2 made an average that resulted in a much higher score. And so now we say setting grouping 2 is the one we want to go with, even though had we not done this, setting grouping 1 would have looked phenomenal. But we looked at those numbers and we went, wait a second. No, we test on all of the data. We start realizing it's actually pretty poor performing. Right. And so it's just because we got really lucky on that first record, perhaps, and we were able to predict it, but we got it wrong all of the other times. Okay. So that's kind of the idea of a K-fold cross-validation, is we fold the data up a bunch, and we ultimately train on all of the data and test on all of the data through the use of multiple model tests using the same settings, but different data. So the main difference between these 5 models here is the data is different each time. The settings are the same, but the data is different each time. We're testing on different data or validating on different data, and we're training on slightly different data each and every time, so that we can take 10 records and actually do this with 10 records and get some better confidence out of it. Okay. But at no time is a model training and testing on the exact same data at the same time. Does that make sense? So I still don't want to train on the testing data, because we are going to create bias. We are going to create overfitting. So this is a way to identify what settings are right. And then what we do is we go, okay, setting grouping 2 was ideal. Let's use those settings. We don't even need to worry about testing at this point, because the tests have already been done. Let's just go train and using those settings and roll with it. Okay. And we can do this kind of at other scales. The more folds of the data we have to match the number of models. Okay. So if I have 8 folds of my data, so 8 minor groupings of my data, then I need to produce 8 separate models to be able to go through this whole process. Okay. And then we're going to get our score, right? And then we're going to do it again with a different set of settings, get our score. Do it again, different set of settings, get our score. So you can do this up to a certain point, but keep in mind the whole reason you do this is when you're working with really, really small data sets where you can't really trust things. Because keep in mind your data sets, they can be really, really misleading based on what you tested with, right? So just one kind of final wrap, hopefully kind of wrap this up a little bit, kind of move past k-fold cross-validation. But I just want to show you one final example of this. So what if, we, again, I'm just going to kind of make some numbers here. Okay. All right. So we have some bigger numbers, and most of them are single digit. Okay. And we've got 10 records here. Okay. So if I take this, oops, gosh, that's getting in my way. Gosh, sometimes I really dislike Excel. Oh, okay, there we go. All right. So 1, 2, 3, 4, 5. Yeah. Okay. So now what I do is I train on that. Train on that. Train on that. I'm sorry, not train, test. Sorry, test. Okay. So do you think like this one right here, the test is going to be that one and this one, or actually these 3 here with the bigger numbers in them? Do you think this one right here, the test results are going to be probably quite a bit different than this one? Because this one I'm only testing on these 2 records that are a 1 and a 2. This one has like a number that's like way out there, right? So my results are going to vary quite a bit depending on which records I test on. So this is why we want to change what we test on each time. And simultaneously, let me change the order of this for just a second. Let me try this, try something here real quick. I'm going to show you something else we're about to talk about anyways. 89, 56. And then we're going to change these down here. So now, let's try this real quick. We'll fill that in. Get what I'm doing here, hopefully. This is also another reason why shuffling your data is going to be really critical. But what if you just happen to shuffle it and all the big numbers are the first couple of records? And so here's what's interesting. Look at A here. I'm testing on these 2 values that are 24 and 89. So let's just say we were predicting a value of some sort or something. The algorithm is ultimately going to be affected by this. This one, I am training on all of that data, right? 56 is the only big number there. The rest of them are all small. And then I go to test it, and I'm expecting results of 24 and 89, right? I'm going to say I want to produce these results based on a training that took place off of that data. It's probably unlikely for me to get a very good score on A. And my score is probably going to be awful, right? Because the test data is so different than the rest of the data. But then I, kind of go through this a bit more, and we go, okay, now I've trained on this data, and I've trained on this data, and I'm testing on this. Now I'm going to get a very different score now. And then same thing here. Now I've trained with all of that data, and I'm going to expect these two results, you know. So you can kind of see as you start to look at the data, you start to realize how this can be enormously important, right? Because if all I did regular simple holdout, and let's say 89 was my test record, and I trained on these, only these, I validated with the 24 and I tested with the 89 and I trained with those, my results are going to be really thrown off. I'm not going to say they're going to be better or worse. They could look really good and they could be terrible, or they could look really terrible and be really good in reality. Okay. So anyhow, I hope that's kind of, you know, just different ways to look at this. Okay. So K-fold cross validation, K-fold cross validation. Just to understand, you know, what this is on the exam, you may come across this. Just to understand what it is, how it works, what it's used for. That's about the extent that we need to know in this class. That's about the extent that you need to know for the exam. But when somebody talks about K-fold cross-validation, you got to know what it means and what it's for. Okay. So actually going out and doing this, it might be fun to kind of play with. Do you need to? No. It's the concept that's important to understand here. Okay. Yeah, you're very welcome. I hope this is clicking with some of you. Some of you may still be totally lost. This is a really difficult topic, and it gets really kind of convoluted. But I hope that's making sense. Okay, I'm going to stop there. Let's take a break. We're definitely break time. We're well past. In fact, I usually like to take a break probably about 10 minutes ago or so. So let's take a break, and then we'll get into a bit more about kind of preparing our data for training a bit more, and then we're going to do some demos and really start doing some training work. Okay. All right. We'll see you back here in let's say 10 minutes. So we're at 10:10 right now Eastern time. Come on back at 10:20. Okay. Have a good break. All right, welcome back. Go ahead and click that green check. Let me know you're back and ready to go. I'll give everybody just another minute. It's kind of a quick break, only 10 minutes. So usually when I do that, people kind of trickle in a couple minutes past. Again, as you're coming back, just go ahead and click that green check. Yeah, you're very welcome, Carl. All right. Well, we'll give it until 1. There we go. 10:21. All right. So let's go ahead and move on. So that K-fold cross-validation is a strategy, not a feature per se. Some technologies out there will perform it for you. SageMaker does have some stuff you can do with K-fold cross-validation in an automatic way. There are some features around that. Okay. So Kip also had a really good question, and it leads me perfectly into the next slide, actually, and that's about shuffling data. You absolutely want to shuffle your data because if you remember my example, I showed you the first 3 records were really big, and then the other ones were all really small, right? I really don't want that to happen, even with K-fold cross-validation. I want to randomize it as much as we possibly can. If it was sorted by size, as an example, sorted by value, those bigger values would all end up together, and I can almost be certain that at least one or multiple folds would be way off, right? I want to try and get them as even as I can, even with K-fold cross-validation. Across the board, we almost always want to shuffle. So I would want to shuffle it, and then like K-fold cross-validation, I'm creating these smaller chunks of data, right? So keep in mind with K-fold cross-validation, let me go back to the one that's K5 just for a little simpler discussion. It's easier to, smaller, less on the screen. Don't forget what I've done here is created a split 5 times. I've split my data up 5 times. So my overall data set, I split it into, in the case of 10 records, 2 records there, 2 records there, 2 records, 2 records, right? I don't know what's going on with my PowerPoint again. Oh my gosh, this is driving me crazy. But you get the idea. So for some reason, the drawing is not happy with me right now. So the idea here is that it's 5 chunks of data. Each one has 2 records. If it was not sorted, we would definitely have chunks of data that were way off from the others. Okay. So yeah, we definitely want to sort, or I'm sorry, excuse me, shuffle. Okay. All right. So here's an example also as to that idea of specific order, right? And shuffling. So small data, small data sets, large data sets doesn't matter. If I don't shuffle, I'm going to lead to what we call bias, right? So basically, I'm training it with one perspective, expecting us to predict the different, right? So as an example, this is a good example with temperatures and months. Imagine if I'm training to try and predict swimsuit sales, right? And I trained it on data from January and I tested on data from July. Do you think my predictions are going to be accurate? No way. No way, right? So I have to shuffle this up. I have to. Okay. If you don't shuffle your data first, you will cause yourself problems. Every single time, shuffle your data. Okay. Now, the nice thing is the tooling with tools like scikit-learn, pandas, and all these other tools that we're using, shuffling is built right in. Okay. I mean, you have to tell it to do it, but you don't have to write a whole bunch of logic to do it. Okay. Shuffling is quite easy to do. So make sure you shuffle your data before anything else, before you split it up for simple holdout. before you split it up for k-fold cross-validation, before you split it up for any activity. You must shuffle your data. Otherwise, again, let's say we're doing 80, 10, 10. The first 80% of your data is going to be in whatever order it is. So if you're taking like a year's worth of data, the first 80% is going to include January through, maybe January through, I don't know, October or something like that. And then your test data is going to be November, or your validation data is going to be November, and your test data is going to be December. And that is going to produce pretty odd results. Certainly not accurate, because I'm exclusively testing on December while I've trained on data all through the spring, summer, and early fall, with a little bit of winter in there, right? So you have to shuffle it so that we have January dates mixed in with July dates, okay? All right. Now, as far as the K size and bias, if you are doing K-fold cross-validation and things like that, K is really just the size of your data. I want to point out K-fold cross-validation is referring to K, but K in this context is not just for K-fold cross-validation. K is the size of your data, okay? K is the size of your data. So whether you're doing simple holdout or anything else, you still have K, okay? So understanding that is important here. So as my K goes up, excuse me, I'm sorry. K is, I shouldn't say the size of my data. I should clarify this just a little bit more. K is the number of chunks of my data, I should say. Okay. So in all reality, it's actually an inverse of size. Okay. So I said the size of my data, but it doesn't mean as K goes up, my data gets bigger. It actually means I have more chunks of my data. Okay. So actually, as a K goes up, the size of the chunk goes down. Okay. So I want to start with that. In fact, if we do look at K-fold cross-validation, this is an easy way to kind of see this. Okay. So my available data is my available data. Okay. So if I understand that here's my available data along the top. Okay. Now I don't know why my drawing isn't drawing, but here's my available data right here. Okay. So it is what it is. The same data is here. Okay. The available data is the same either case. But as I make my K bigger, the chunks are going to contain less data in each chunk. Okay. So just kind of help clarify this a little bit. All right. So as K goes up, which means the number of chunks goes up. Okay. The time it takes to do this goes up, especially if we are talking K-fold cross-validation, because I'm going to have more folds, which means more models have to be produced. Okay. So again, if I look here, I'm making 8 models, and I also have to have a lot more chunks that I'm working with. So it's going to have to kind of roll through this data a lot slower, right? This one, I'm doing only 5 models, not 8 models. Okay. So as the K goes up, the time goes up. Error variance in my test data goes up. Okay. This is because I have more likelihood that I have a test chunk that's got very unique data in it. If you remember my example earlier, do I still have it up, or did I think I killed it off? Yeah. So with my spreadsheet that I had those like larger 2-digit numbers, and then I had a whole bunch of single-digit numbers, right? If I had K10 and I only have 10 records, and I test on one of those that's like 98, and that's my test record for that K, I'm gonna have a huge error variance, right? So each time I roll through a K, I'm gonna have very wide swaths of scores, right? So that's why I need to average it out when I'm done, because right now I'm gonna test on a record that says 98. Well, most of my records are like single digits, you know. So my error variance goes up as well because it's the test is not going to be as diverse. If that makes sense. So time goes up, error variance goes up. However, bias goes down because I am taking smaller chunks. I'm going to train on a much smaller chunk, and I'm of course averaging it all out when I'm all done. So I end up getting, again, stuff all over the board, and then I average it out, and I end up something in the middle. Bias is like kind of forcing us in a particular direction, right? So if you remember, we said if we go back to this slide right here, this is bias, right? Rather, let me go back. This one right here, this is bias. Okay. So if I have a bunch of records grouped together that is not randomized and I don't have a very high K value, then I'm going to have more bias because I'm going to be grouping a bigger chunk of data together at that point, right? So the less I group stuff, the more kind of smaller sets of chunks of data I have, the less bias I'm going to end up with, because it's going to be a lot more variable. It's going to be a lot more variance, but then I average it together and it kind of ends up where it needs to be, right? So less bias. But again, with a higher K, it's going to also increase my time. So my time is going to go up, my error variance is going to go up, but my bias is going to go down. So this is kind of the general idea. Again, for the exam, might be a good idea to know this behavior. As K goes up, bias goes down. As K goes up, time goes up. K goes up, error variance goes up. Okay. No, Kip. So it's randomized, but I still don't test or validate on the same data I'm training on, ever. Look at this right here. This is still randomized. I want to point that out. This is randomized right here. But model 1 does not validate on the same data it's training on. Model 2 does not validate on the same data it's training on. Model 3 doesn't, and so on, right? So no, we should not have validation show up in our training data. Validation or testing data is still separate. No matter what, it's always separate. We never want to train on the same data we're testing on. Okay. It's really crucial. And again, I mean, if I think this is in that case, that's kind of a fairly simple thing to understand, because machines learn the same way as humans in this sense. Okay. Oh, across faults. Yeah, absolutely. I mean, in this case, you're still gonna ultimately test on all of the data, randomized or not. You're testing on all of the data, or validating in this case, right? Validating across the data, all of it. But randomized is going to make sure that you don't end up with, ideally, in theory, you're going to be less likely to have a single validation that has grouped data, right? What I don't want to do is end up with one of these validation steps with data that's all together, if I can avoid it. Right? Now, again, it's by chance how I randomize. So there's actually even more advanced stuff that we can do than this. We're actually going to show you some examples of it without going into crazy depth here coming up. But I think we've talked about this enough. So again, best practice, randomize your data. Now it looks more like this. We start to see, and this best practice is not unique to K-fold cross-validation. It's across the board. We should always randomize our data. Okay. Now these are some variations. Now we start to see how crazy we can get here. Okay. If we want to increase, we're going to increase time doing this, which also time can equal resource consumption, which can equal cost, actual, financial cost potentially, because we're spending more time doing this stuff. But my bias is going to keep going down, right? I'm going to keep reducing bias, and that's really the important part. And we'll talk about bias in more detail. So we've mentioned the word bias quite a bit. Some of you may not be quite sure what that means. We'll show you here coming up. But so here's where we actually do a K-fold cross-validation with multiple iterations. So now what we do is I want to point out, this is all using the same settings for this setting chunk, if you will. Okay, I'm trying to kind of be generic here. And then I would do this all again for another settings chunk, and do this all again for another settings chunk. I want to point that out. The point what we're doing here is mucking with our data. We're making sure that we're getting as much, we're playing with our data and trying to avoid as much bias as possible. Okay. And so we're going to do, this is like k-fold with K3, but we're doing it with 3 iterations. So what we're doing is we're creating K3. We're doing 3 chunks of data, right? And we're training and validating on all 3 chunks across 3 models. Then we do a whole fresh randomization. And then we make 3 chunks again and do 3 folds again. And then we randomize it all again, and we do it again. And then we average the scores of all of that. The point here is to just try and get as least bias introduced as possible. So randomization, as I mentioned, the goal here is to make sure that, like, I don't want a validation chunk of data to be biased. I don't want it to have a chunk where it's, it's got those 2-digit numbers and then the rest are all single-digit numbers, and it's really going to be off, right? Well, that might happen with iteration 1, but then when we re-randomize in iteration 2, we should eliminate that problem, right? You see what I'm getting at? And then we're going to do it again in case there's a new variation, a new bias that was introduced in iteration 2 because of the grouping. Then we do randomize again. We do it again. So you can kind of start to see how we're trying to avoid groupings of data that can mislead us, right? And when we have really small records, that's exactly what happens, right? Imagine if I have 3 records. Now, I mean, again, can you train on that? It's probably not, it's not going to result in amazing things, I don't think. You could try, okay, but we're certainly not going to want to do simple holdout. That wouldn't make any sense. And we want to train on all 3 records, but then how do we test it? So, this would be a way to kind of just randomize. Now, 3 is probably extreme. We're almost never going to do anything with 3. But 10, I've seen models created with 10 that are highly successful with just 10 records. Just 10 records. But it's about applying the algorithms over and over and over and over again to this stuff. But don't forget, each one of these models, you have to really kind of think about what's going on here. There's a lot of processing happening here because each one of these models is going through the model creation process, which is adjusting its weights. It's running through an algorithm, adjusting its weights, going through the algorithm, adjusting its weights, adjusting an algorithm, going through its weights, and then validating, right, through that process, and then producing a model. And then it does it again for model 2 and model 3. And then we're completely changing our data, still using the same data, but we're changing the data arrangement and then doing that all again. And then changing the data arrangement and doing it all again. And then we're averaging all the scores so that we could hopefully avoid any kind of bias. All right. Other variations, leave one out, cross-validation. Test set is just one data point. Again, really small data sets. These are other variations. We're not going to get into any more of these details. We pretty much hit this one hard enough. And then another one's called stratified k-fold cross-validation. Training and test sets balance class distribution. So remember, class distribution, the idea there is, for training for fraud, half the records should be fraudulent and half the records should not be, so that we have even class distribution. So class imbalance is a problem for us a lot of times. So when we have highly imbalanced data, we can apply some of these strategies to help us with that too. Okay. So maybe we don't have 50% examples. And so we need to, work with strategies that can help us with that. So we're just kind of calling them out here. You can go research them more on your own if you'd like. But we're just kind of saying, look, there's a bunch of different strategies here we can apply. All right. So to go about randomizing your data before training, scikit-learn has this, built right in. And you can specify a train test and, a train test split. You probably already saw this in your code somewhere yesterday or the day before. It was in there, but whether or not you noticed it or really paid attention to it, but it was actually, I take that back. Previous labs, I don't remember if you did this or not. It may not have been. I think the data may have already been set up for you. But yesterday, I think you were doing your pre-processing. I believe you did some of this. But in all reality, we need to go ahead and shuffle the data, stratify the train and test data sets. Okay. So just kind of some visuals using actual numbers now. I already kind of wrote some of it out myself, but the idea here's a simple holdout. You got all of your data. You take a chunk for training, a chunk for testing, a chunk for validation, right? And then we could do something like 3-fold cross-validation. Here's where fold 1. You've got, again, this is the fold 1. So just to clarify the fold. If I go back to show you the example of this one. We're talking about this right here, the iterated k-fold cross-validation with shuffling. So you have iterations going on here, right? So to kind of give you that example, we have different folds. We've got our train, test, validate, train, test, validate. You see the change. So the records, I want to point out the records between these folds aren't different. You'll notice, 23, 43, 12, 23, 43, 12. The order is the same here. We're color coding them to kind of show you how the arrangement changes, right? So my training data on fold 1 is different than my training data for fold 2 and is different from my training data for fold 3. My validation data is different for each one as well, and my test data is different for each one as well, okay? Same data set, okay? And then they iterated, okay? And then again, more on that. So I think we've hit this one pretty hard. If you're not getting it at this point, you just need to take a break from it and then come back and revisit the topic because it is a complex beast to really kind of grasp at first. But I think once it clicks, it's not awful, but it's a tough one. Okay, so model training. So we have features. Don't forget, what are our features in this case? We're talking about our dimensionality of our data. We're talking about columns, right? A feature is a column typically, and when it comes to like producing CSVs and things like that, a column would be a feature. We have labels that are also going to come in if it's labeled data, right? If it's supervised learning. We're going to have some sort of model we create when we're done training, right? It's going to produce a model. We're going to have inference. The actual act of inference means predictions. Okay, so just understand the words here. When we say make a prediction, it's called an inference. All right, the official term is inference. Now we have what we call this compute loss function. We're going to talk more about this coming up here. We're going to try and find the least errors. So in other words, as it adjusts those weights I've been talking about this whole time, we want to see if the errors get better or worse. We want to find the least errors. We want to find what we call our minima on errors. We're going to have a compute loss function for that to help us calculate that. So we'll talk more about that. So first off, let's say we've got this data here. We've got our target variable and our feature. There's different kind of swoops, different paths we could show you. A human could draw it, but a computer doesn't see this visually, not in this context, right? The computer sees the values, it uses mathematical equations to actually understand these variables, okay, as we adjust these variables and whatnot. So computer generated may not be, it could take different paths here. And this is going to be based on our weights, our variables, okay? Those weights that we're going to adjust how it sees this, right? And how quickly it adjusts, how quickly it pivots. This sharp turn that happened here, the algorithm needs to realize that it's, it needs to make an adjustment and go the other direction, but how soon, right? This one did it really late, and this other one did it really early. And maybe we need to find a place in the middle somewhere, right? So there's this what we call a loss function. And again, we're trying to find, and so I want to clarify what we're talking about with errors here. We make a pass through the data using a particular weight. Now you have a starting point, okay? So the weights are just a variable, and it's a starting point. The first time through, it doesn't know really anything. Okay, so the first time through doesn't really do us any good. And this is within the training process. I'm not talking about producing a model yet. This is during the training process. It's not going to produce a model yet. It's going to go through this many times before it produces a model. Okay, so it goes through it and with this variable, this weight, and it gets an answer. Then it makes an adjustment to that weight, and it does the algorithm again, and it gets an answer. Is the answer better or worse to reality, to the correct answer, right? So did we get worse or better? So this is an error rate, if you will. An error would be we predicted it's something that it's not. That would be an error. Or we predicted that it's not something when it is. Okay, that's also an error. In other words, accuracy. How many times was it right or wrong? Okay. And so as it gets better and more accurate, it knows that we're adjusting that weight in the right direction. Okay. So keep adjusting it in that direction. And then at some point, so let's just say the optimal number for the sake of discussion is 25 on this value, this variable. Okay. So 25. It starts at 5 and we get some value, and then it makes a tweak and it changes it to 10. And it gets an answer. It goes, hey, we got better. Keeps going. It gets to 25. Okay, looks good. Then we go to 30. And then 30, the errors started increasing again. And then 35, they increased yet again, and they got worse. So we, in theory, in that example, found our minima. Our minima is, at that point, 25. Okay. 25 has the least amount of errors. Okay. And now it's going to stick with that and produce the model. Okay, now we're going to say, cool, here's our model. We're going to use the weight of 25. All right. So that's what we're going for. So have the system find the minima of accuracy, of errors, which result in accuracy, right? So there's these different loss functions that we can use to help identify this, right? Basically, you have root mean squared error. Now, some of these things, we don't need to memorize these formulas. Okay, I highlighted this the other day. Don't memorize the formulas, but understand what some of these things do. Okay, so simple loss function, root mean squared error, RMSE. If you see this, you need to kind of understand what it does. Don't memorize the formula. Just know if you see this, it's basically describing the standard deviation. Okay, between predicted and observed. Okay. I predicted that this was true and it was actually false. Okay? Or I predicted it was true and it was true. I predicted it was false, it was true. So what's the difference there? What's the standard deviation? So it's calculating that standard deviation. Then there's also log likelihood loss. This considers the logarithm of the probabilities. Okay, so again, a little bit of math, science, mathematical science algorithms kind of stuff coming into their play there. We don't really need to memorize those things, right? So again, the minima is the point where the least amount of error exists. All right. Now, how do we find the minima? We can optimize this parameter. Okay. Well, the algorithm optimizes the parameter, I should say. Okay. So this parameter is a variable like weight. All right, so we adjust the weight. It's a variable in the algorithm. It applies that parameter value, see what our answers are, change the value, see what our answers are, change the value, see what our answers are until we get to the least error, right? That kind of idea. All right, and this is optimization. Now, optimization is happening through the algorithm, and this is going to be based on some input parameters that we can give it. Okay. So here's the thing. There are two things that use the word parameter. If I just use the word parameter, it's something that happens inside the algorithm that we don't have control over. This parameter is not set by us. We might set the initial starting point, but from there, the algorithm runs with it. This is the training process. The parameter is adjusted. That value in the algorithm is adjusted each time it goes through the data. Okay, each time it goes through what we call the epoch. We'll get into that in more detail in a minute here as well. So we have this search for the global minima. That is what we're trying to do. We're trying to find the least errors. Now, there's some traps we can end up in. We can also find ourselves getting stuck in what we call the local minima. And the idea there is that, you're running an algorithm and you're making tweaks and changes. I think this slide should be switched, like to make it illustrate it better from left to right. It'd be nice to see the local minima on the far left and then the global minima on the far right, because as you're going through this, it's possible that you see, hey, I was getting better, and then we got worse again. So the middle value right here, that's our minima, right? No, It's not really our minima. It's just that the way the calculations worked out, it kind of created a wave. And this is the way things work in reality. You'll find that you can get stuck in these local minimas when in all reality, the best value is over here, right? And so this is stuff we have to worry about. Now, again, a parameter is not set by us. It is set by the algorithm as it goes through its tweaks, as it goes through its iterations, as it's creating a single model. Okay. Again, the process is it goes through this algorithm with a weight, goes through it again with a different weight, goes through it again with a different weight, and keeps doing that until some stop point exists. We'll talk about that in a second as well. But when it stops, it says, what was my least error? Use that weight, produce the model. All right. Then we have another thing that has the word parameter in it, but it's called a hyperparameter. We'll get to that in a minute or just a little bit. Hyperparameters are settings that we set ahead of time. So we as users of the system, right? So these are inputs. Hyperparameters are inputs, or I was using the word settings earlier. So when I said groupings of settings, it was really groupings of hyperparameters that we're going to feed into the system to perform our training. And these are going to be settings. They really are settings. Hyperparameters are basically settings where we say, here's how we understand our loss. Here we're going to use certain loss functions or log functions. We're going to take this kind of step size, what we call learning rate. We're going to set some of these things, and they can all have a big impact on our final result. Like I said, we can get trapped in this local minima right here, which can be a result of my hyperparameter settings because of certain activities I tell it to use, certain decisions that I've made to tell the algorithm how to behave. Okay, so hyperparameters are settings that the algorithm will leverage throughout its process, and those can have big impacts on my accuracy of my results. Okay, so comparing all possible values would be inefficient. Okay, if the minima is way down here, let's say, like I said, imagine the minima is 25, using that same example again. And I start with 1. I start with 0. Say I start with 0. And I tell it to increment by 0.01 each time until it finds the minima. And it has to run through the entire data set each time. How many iterations will we have to get through to reach the minima? And I'm not asking anybody to actually do the math. It's a really long time, and it's a lot of processing power. Okay. This is where you could make a training process last as long as you want. Even if I've only got 10 records, I could train on those 10 records for the next 5 weeks on one model creation. This could run indefinitely. I could say, go ahead and start at 0 and adjust the weight by 0.000000001 each time incrementally until you get to 25. And I'm not going to tell it to get to 25. I'm just saying if 25 ultimately is the right number, it's going to have to go, and it's actually going to have to hit 25 and go well beyond it before it understands that that's the minimum. Right? I mean, we could go for years on even just 10 records. Okay. So this is where we're not going to do that. Okay. We need to understand what size jump do we want it to try. Okay. And what that's really called is a learning rate. So maybe instead of starting at 0 and, going 0.0000001 each time, adjustments, right? We may go from 1 to 2 to 3 to 4, or 0 to 5 to 10 to 15 to 20 to 25. Bigger jumps have pros and cons behind them, right? Too big of a jump, and we could skip the minima altogether. Too small of a jump, and we don't get to the minima in the time that we need to get it to. Okay. So we got to find a balancing act here. And then also where you start from. So maybe I don't want to start from 0. Maybe I want to tell it to start at 10. Right. And so that's all inputs that we can tell it. And that's the tricky stuff, to be honest. That's the tricky stuff of this. The nice thing about SageMaker is we don't need to worry about all the other moving parts of machine learning. We can just tell it, I want to use that algorithm, and here are my inputs, my hyperparameters. And to make it even better, we can actually automatically select our hyperparameters through SageMaker as well. It can do that work for us. We'll get to all that later. Okay. Okay. So this is very inefficient to try and do it, one little tiny micro change at a time. So we're probably going to make bigger jumps, and we could either just do a fixed bigger jump, right? Or use algorithms to do this. Things like gradient descent. Gradient descent is going to understand the descent or the shape, if you will, here, right? So if it's a steeper part of the curve, it can take bigger jumps, right? If it's a more shallow part of the curve, it's going to speed up, or it's going to do more aggressive smaller jumps, right? So, bigger jumps as we go. And then as it gets closer to the minima, as it starts to flatten out, it might go more incrementally and then bigger again, right? That's the nice thing about gradient descent. Okay. Yeah. Yeah. Genevieve had a question in there to me privately. Yeah, there you go. So there's strategies. And again, we can choose this. We can tell it to use gradient descent. But even then, there's multiple flavors of gradient descent that we can choose from. So again, these are all inputs. These are all things that we, as the data science part of it here, is our job to kind of play with, right? To kind of play with some of these different settings and kind of see where we get the most accurate. And again, I want to highlight, what are we doing here? We're finding the least errors. What is an error? An error is we guessed wrong when it was one answer, we guessed a different answer. So find your least errors. Find the weight applied to the algorithm that is the optimal weight. Okay. And then now what we do is new data, once that model's been created, new data comes in, that weight is used because that's built into the model. That weight is used for predictions. Because that's part of the model creation is it generates the model based off of that weight. Okay. So gradient descent optimization, it'll get more. Yes, this is a hyperparameter, Odette. Yeah, absolutely. So you can choose gradient descent as one of your choices here. Okay, absolutely. And so again, here's our minimum. Okay. The learning rate is what we're talking about here, really. If we go too big, so again, you have learning rate combined with gradient descent. There's a combination of these parameters, these hyperparameters, combination of these hyperparameters that really kind of make up the results here, right? So even if we're using gradient descent, still we're going to have some values of gradient descent. Like how aggressive does it get at the low point of the curve, right? How aggressive does it get? How big of a step are we using here? That size of the step itself, the overall size of the step, is called a learning rate. And the bigger the learning rate, the faster we'll probably get our answers, but the less accurate the answer will probably be, if that makes sense. Because we're going to be able to just fly through these values, right? Big chunks. But you see here, we never actually got to the minima. We skipped the minima. As far as the data is concerned, as far as the system's concerned, that's the minima right there. That was the lowest value, right? But we missed the right value, which means we could be more accurate here than we are. Right now, it's probably performs okay, but the model that this is going to produce is probably not as accurate as it could otherwise be. Okay. But on the flip side of it, if the learning rate is too small, just like I was talking about, we're just going to run out of time. At some point, we're going to say, I don't want to train for the next year on this one model. At some point, we're going to have to call it, and we're going to say, I only want this to train for the next 5 minutes, the next 2 minutes, something like that. Let's see what we can do in that time frame, right? So if the learning rate's too low, you're probably never really going to reach your minima, right? So, so again, that's kind of what we want to get as the minima. As we get closer to the minima, we want to use a smaller learning rate, and that's the whole idea of gradient descent, right? But again, even gradient descent, again, how aggressive are we going to be here? Okay, there's still a factor there. Gradient descent's not just a magic thing. Okay. So updates. Okay, so gradient descent and the way that standard gradient descent works. I've been talking about this whole idea of what we call an epoch. I just used the word for the first time a few minutes ago. The epoch is a run through the entire data set and then the weight gets adjusted. Okay, I've been using that example this whole time. So it gives it you put in a weight. We don't. I mean, we might give it a starting point, which is a hyperparameter, but the parameter is the weight, and that's adjusted by the algorithm as it goes. Okay, the parameter only gets adjusted by the algorithm at the epoch. And with gradient descent, the epoch is only after it's gone through the entire data set. So you can see how this is fairly inefficient, especially if this is a really large data set we're training on, right? And the other problem with that is that entire data set needs to be able to fit into memory. The entire data set has to be able to fit into memory. Small data sets, this is fine. Huge data sets, this is a problem, right? Also, gradient descent, normal standard gradient descent can get stuck at that local minima. It may not reach the global minima. Just some things that regular classic gradient descent can suffer from. Okay. So there's actually variations of gradient descent. Okay, there's three primary variations that we can select in SageMaker that are commonly used in the industry. Okay, regular gradient descent, the weights, those parameters, those weights are updated at every epoch, the entire data set. Okay, that's the slowest. The gradient steps are going to be very slow, or it's very smooth though, towards that minima. Okay, then we have stochastic gradient descent. Every single data point, it has the ability to adjust the weight. Okay. This, however, you're going to end up with a big zigzag. Okay. So if I were to draw it out with stochastic gradient descent, it'll probably, look like this as it goes. And then, okay, there's my minima, right? But it was very erratic to get there. It was very erratic to get there. Okay. So it's very noisy, very erratic. And again, erratic can mean compute resources, can mean more time is weighted as it's kind of bouncing around, right? So still, it's going to be faster though than gradient descent. In fact, it's way faster. But again, you may not really get to the right minima perfect as cleanly. So mini batch gradient descent is kind of a nice balance between these two, because as the name implies, mini batch. So what you're going to do is you're going to create, you're not going to create it. The system does this for you automatically. But, just for the sake of very basic understanding here, if I have 1,000 records, maybe it takes 10 records, maybe it takes 100 records, and it tries to look for the minima. And then at the end of those 10 or 100 records, whatever they are, then it can adjust the weights and try the next, adjust the weights, try the next, adjust the weight. It's doing chunks. Okay. Keep in mind, your stuff is all randomized, right? So these chunks are all completely randomized chunks of data each time as it goes, and it's continuing to try and find that minima. All right. So this is, instead of the entire data set, you're going to take smaller chunks of that data set, versus stochastic gradient descent does every single data point. And so you kind of end up with a blend of both with that mini batch gradient descent. It's not the slowest, it's not the fastest, it's kind of in the middle. It's less noisy, less erratic towards that minima. It's a little bit cleaner path. And so you kind of find that middle ground. Okay. So in all reality, all of these are options. Okay. You can choose any of these. Also, I want to point out the batch size of many batch gradient descent will be a hyperparameter setting. So the size of the batch could play a role, not just in time and performance, but actually quality, right? A bigger batch versus a smaller batch size may result in more or less weight changes. And more or less weight changes means I get to that minima more or less effectively. So I may end up with, I may want to test different size batches with my success. My accuracy could be dependent on the size of the batch. So these are all things that impact the quality of my model, the performance of my model, the accuracy, loosely speaking, of my model can all be tweaked by these settings, these hyperparameters. Okay. So pretty much all of your algorithms found in SageMaker you can select these different gradient descent options. All right. As far as running your training job,
Ryan, can I just ask a question real quick, please?
absolutely, go for it. Jump in.
So the gradient descent algorithm, that's part of estimating the loss. Is that right?
That's
To
correct.
minimize the loss. Okay, and so you say it updates these weights, every epoch or every data point, depending on which weight descent used. Are these the parameters? Or are these hyperparameters? Like, kind of where in the chain does this algorithm sit?
Okay, yeah, so great question. So just to recap on that, these are parameters. A parameter is a weight. It is that variable that gets adjusted within the algorithm during the training process. We don't adjust it.
Okay, right. And so this is within the model? Is that right?
This is during the model creation, the training process. Okay. Yeah. So you initiate the training process. You're going to give it some initial inputs. Those initial inputs would be your hyperparameters. And those could be things like what learning rate do you want to use? What is your, do you want to use stochastic gradient descent? Do you want to use mini batch gradient descent? If you're using mini batch, what's the batch size? All of those things, right? And then what do you want to start at for your weight? What's your starting weight? And then we say go. And the algorithm now takes that starting weight and it's going to start adjusting that starting weight. Okay, it's going to start with something, but that's it. It just started with it. From there, it's going to run with it, and it's going to try and adjust that weight each and every time it can adjust it, trying to find the most accurate weight, the weight that generates the most accuracy or the least error. And so it's adjusting this weight. This is a variable in the algorithm. And so it's constantly changing that weight value. And don't forget, what's happening is that algorithm is applied to that entire record, all the different features that make up that record. This is why I was saying, looking for patterns in the data. You're not looking for just some arbitrary pattern. It's a pattern based on the algorithm's output at that point. And so the algorithm is applied to the entire record with a weight applied. And then same thing again, run the algorithm with a different weight applied and see which one resulted in more successes or least errors. Okay. And so that's the general picture. So the weight is something that adjusts within the training process by the algorithm. Hyperparameter, and that's also otherwise known as a parameter.
Right. And so gradient descent, that's kind of something that's going to be our loss estimator, right? So that's a standard feature that as we're training a model, we're setting things up, we're going to, choose some kind of gradient descent, or maybe there's some other function, but it's to us through SageMaker, from our perspective, it's just a standard piece of the machinery that we choose, right?
Yes, it's a hyperparameter. And that's not even a SageMaker feature per se. That's a hyperparameter for the algorithm, whether you do it in SageMaker or anywhere else. It's an input where we're saying we want the algorithm to leverage gradient descent to find that minima.
Got it. Okay. Thank you.
Yeah, absolutely. Yeah, very good questions. So big picture there, we are instructing the algorithm how to get to that minima, and we have control over the approach. But then once we tell the algorithm, here's the approach, again, that approach can consist of learning rate, gradient, selecting kind of, the flavor of gradient descent, the batch size, all these, the starting weight. And then from there, we've told it the approach. Then the algorithm kind of takes it from there and says, okay, following your instructions, it's going to go through those adjustments for you. And that's just part of the training process. So the training process then goes through that. And again, how it goes through it is based on what you told it to do. Yeah, great questions. So awesome. Yeah, so that's some of this stuff. This is pretty heavy stuff. I mean, if you're new to this, I mean, some of you have been doing this stuff for a long time, but if you're new to this, it's a lot to take in. So I get it. It's going to take some practice, some understanding, for it to all really kind of sink in. But like I said, the simplest way to think about this is just imagine just a calculation, an algorithm applied to a row. Okay, it takes the features as inputs, it's part of that, process, applies an algorithm to it. The algorithm has a value, has a variable, and we adjust that variable, and we look at the result, and we adjust the variable again. We look at the result, keep adjusting it, and we want to try and find when the results are as best as they can be, and then that's our model.
Oh, sorry, one more question. So it sounds
go
like
for it.
we also have to have some method of evaluation or like a fitness function or something that says, okay, this is our optimal value, or this is kind of what we're expecting. And
Yes.
what is that? Where does that come from?
Gotcha. Well, so optimal value, it doesn't stop. Okay. So yeah, it's a hyperparameter. Actually, it's an input. Well, you'll see. I'll show you some demos, and we can actually say what we want for, what we consider best, if you will. As far as that goes, that's part of our testing process too. So, what score are we going to rely on to consider this good? So we're going to have to talk about the terms accuracy, precision, recall, all of that kind of stuff, which we'll get to understand what is considered accurate, because and then we'll be able to kind of tell the model basically that's what we want to use, because ultimately, how does it know if it's, if it starts out, so as it's going through, it's looking for, it's just regular accuracy. It's trying to say, were we right or were we wrong? Okay. And so at this phase right here, this whole phase of the training process, it knows the truth. So assuming it's like labeled data, just kind of, that's the simplest one to talk about is supervised learning. For this example, it already knows the answers. So our validation data already has the answers. All this phase right here is actually really trying to do is get as many of those answers correct as it can. So that is the measurement right now. At this phase, it is about, okay, with this weight, we got 9 out of 10 correct. With another weight, we only got 8 out of 10 correct. Right. And so it's a pretty straightforward measurement there of right or wrong. You got it right, or you got it wrong, or how close to right or wrong you got. Okay. So if it's a number like regression problem or something, how close to the number were you? Right. So we already know the real number. How close to that number were we? Right. And so that's what it's looking at. Ultimately, that error rate is really simple. The error rate is just got it right or not. But when we go to actually evaluate the model ourselves and to see if we're giving it the right settings, we're going to have to understand accuracy, precision, recall, some of these other things, these F1 scores. These are scores on different ways to understand if it's good or not, or successful or not. So the model will say, here's the lowest error. But we need to look at it and say, after the fact, and say, okay, based on that model that got produced, is it successful in our measurement of success? Because sometimes we might be willing to be wrong more often to be right more often. And this is where things get a little complicated. Remember my example. I'm not going to go too far into this right now because we're kind of jumping ahead. But let me just state this and just kind of wrap it for right now, and then we'll come back to it. But the example where I said fraud, if fraud's 1% of the time, I've got 1,000 records and 10 of them are fraudulent, and I do a training job and I come back and my quote unquote accuracy is 99%. It didn't have to do anything other than say it's not fraud to achieve 99%. That's because what I considered successful is different than just overall percentage. Because what I may want to look at is how often was it correct when it came to predicting the fraudulent transactions. And now I look at that and I go, whoa, it's 0%. So that's a completely different measurement. The training process doesn't necessarily look at that, because the training process is just simply looking at it from out of all of these records, what's the percentage of right versus wrong, and what's our error rate, so we're going to look at it in the testing process a little bit more intelligently than that. Okay. And so if we look at that and we go, this model's terrible, it's because we need to look at it. We need to probably have some different inputs or some different tweaks on the hyperparameters to get us to the thing we actually care about. So we might actually be willing to be wrong more often and actually have a lower overall accuracy if it means my fraudulent transaction accuracy goes up, if that makes sense. So there's more to this, a lot more to this. So for now, just know that the training process itself is really the error rate is really just something very simple. It is percentage, basically in all reality, kind of, equivalent to like percentage correct, okay, or percentage wrong, I should say, because we want to get the lowest error rate. But that doesn't mean the model is optimal for us. And so we're going to use the hyperparameters to tweak that so that we can generate a model that is in alignment with what we want. Awesome. Okay, so running our training jobs, we're going to have multiple SDKs we can work with here. There's a SageMaker specific SDK that's just for SageMaker. And then you also have your AWS SDK, which is kind of everything AWS. So the AWS SDK is what I would use to, let's say, interact with S3 buckets, interact with my, maybe even to, like, let's say, launch a notebook instance even. I could automate that. Or to automate a training process or something. I could use a little bit of the AWS SDK, but really we start getting into the SageMaker specifics. I'm going to use the SageMaker SDK, and I just misspoke. I would really use the SageMaker SDK for the actual training process, but I would use the AWS SDK to set up the data. If I'm doing things like EFS, the Elastic File Storage, remember we talked about that, or FSX for Lustre or something, that's all going to be done through the AWS SDK. Whereas SageMaker, anything really specific to SageMaker interactivity is going to be through the SageMaker SDK. So we'll kind of talk about real quick the architecture of SageMaker a little more again. I already kind of talked about this before, but again, we have built-in algorithms with SageMaker. Keep in mind, these are coming from a container model. So really, nothing here actually exists. This is a framework or a shell that's kind of dumb on purpose, and it's pulling in these containers to provide this functionality. And you can replace, one of these containers with your own, and it just comes in that way. Okay, so just kind of understanding that as we go through this discussion. So we have our data. We tell it, hey, here's where our data resides. It pulls the data in, runs it through the different algorithms or frameworks and things like that, and it produces a model, and the model gets put, as my output. Okay, my input's my data, my output's my model. All right. So I can, again, layer these things. Okay, so I could do a custom script here. And so this is actually, I'm able to replace the algorithm without necessarily replacing the framework if I don't want. if I don't want to replace it. So a lot of people get confused by this one, especially really experienced machine learning people. A lot of people kind of think that the algorithm and the framework go together, and they don't have to. I can run XGBoost or linear learner on many different frameworks. I could run it on TensorFlow. I could run on PyTorch, right? So so the frameworks are separate from the algorithm. All right. So if I want to supply my own algorithm or my own custom script that includes whatever algorithms I want to include, so I could go download some algorithms from some third parties, put them in my own custom script and put them in here, and still tell it to just use, hey, SageMaker, go ahead and just use TensorFlow to do this. I'm just going to have my own custom script that works with TensorFlow, and that's all I have to worry about because TensorFlow is already installed, already working. I don't have to do anything with it. Okay. So these are different engines that, frameworks, we call them frameworks, really kind of different engines to perform these algorithm activities. Okay. The algorithm is separate though. The algorithm is the actual algorithm. Okay. It's the mathematical equation. It's the actual math that's taking place. Okay. And then we could also replace the framework if we wanted to as well. Okay. So we could go modify existing Docker images for our own use. We could enhance them and change them. We could also just completely use our own if we wanted to. So you can go build these Docker containers anywhere you want, put them in the repo in AWS ECR, and tell SageMaker to use them. So any level of customization you want to do here, you can do. Okay. And so you can also go to the marketplace and it does the same thing where you go to the marketplace and some third parties have already created those Docker images for you. So there's third parties that are, specialty to the financial space as an example, and they've already created very custom algorithms or models for that space. And you can just go to the marketplace and use it. Now there's open source in here that's free. And then there's also paid commercial stuff. Okay. So you can pick kind of any mix and match of these options that you want. This is what makes SageMaker so amazing is you can just use the built-in or you could do your own. Now, here's the thing. One thing I have also encountered quite a bit over the years with SageMaker now is a lot of really brilliant data scientists, some really brilliant machine learning individuals that really know what they're doing. And they immediately kind of jump to this landscape. Why? Just because you know what you're doing doesn't mean you should make more work for yourself. Okay. The more work you create for yourself, also the less support you create for yourself as well. So keep that in mind, because if it's something completely custom on your end and you contact Amazon because things aren't working the way you want them to, do you think Amazon's really going to be able to support your script? It's going to be questionable, right? They'll take it to a point, but at some point they're going to be like, you got to fix your script. You got some stuff in there it's pretty bad. So the more built-in stuff you use, the better. And these are these built-in features and frameworks and stuff. They're all industry standard. None of them are SageMaker specific. Okay, they are all industry standard things. So if you're using XGBoost as an algorithm on premises and you select XGBoost in here, it's identical. Why on earth would I bring it in custom at that point? It's kind of pointless. Same thing with frameworks. If you're using PyTorch on prem and you're telling it to use the PyTorch framework in here, it's the same thing. Okay. So the beauty is SageMaker's built-in stuff probably meets a good 95+% of the machine learning challenges or problems that we are encountering and we're trying to solve. I don't need to do anything custom most of the time. Okay. The fact that custom exists is great, but I think sometimes it becomes a problem of its own because people like to just, they feel like they want control, I guess. There's a lot of, a lot of times it doesn't hold up to a lot of logic. Like if you start asking why you're doing that, I just want that flexibility or whatever. Well, if you need the flexibility later on, then great, but why are you doing it right now? Is there something specific that you can't do that you have to do for what you're trying to do? I don't know, right? So the built-in stuff is going to handle 99%. I said 95 earlier just to be cautious. Probably 99% of the situations out there are just going to be fine with the built-in, but I'll say 95+% just to just to give myself some wiggle room there to say, okay, maybe there's some edge cases where you need to go custom, but SageMaker's built-in stuff is going to handle the majority of what you're going to encounter. Okay. And then you can go to the marketplace, and there's a whole bunch of different industry segments that are handled in here, a bunch of third parties, a bunch of commercial stuff that's in here, very specific, targeted. It says model packages and algorithms. Let me explain that one real quick. So algorithms would be something you would use to create a model of your own. So you would use your data and run it through the algorithm to produce a model, right? You can also, however, find models on the marketplace, meaning you don't have to create the model. And those are going to be more commonly found with like public data that has been trained. Okay. So in other words, I don't know, just in kind of modern days, maybe you want to do some stuff with COVID research and things like that. And so there's public COVID data sets that have been actually published out there. Of course, there's no personally identifiable information or HIPAA data or anything like that in them. It's just, randomized data in that sense. But there's COVID data out there. And so if somebody wanted to do something with that, there's actually models that have already been created using public COVID data that you could run your own data through to make predictions against, right? So you don't even have to create the model, and you could just go get it out of the marketplace. Now, it's probably going to be for a fee because somebody else did the work. You're just using their model. Okay. And I'm just using COVID as an example. There's space stuff, there's financial stuff, fraud detection stuff where, others have already created the model. Now, this doesn't carry with it any real risk in the sense that what is a model? A model does not contain any data. It has been trained on some specific data, but it does not contain any data. So sharing models with somebody, there's no like security risk there. Okay. Not in that sense. It's making predictions or inferences based on data you're going to send through it. It'll make predictions. And the question is whether or not it's accurate, right? That's the big discussion around a model. Is it accurate or not? And again, what means accurate? We'll have those discussions coming up. Because like I said, my example of fraud with 99% accuracy with 0% accuracy around the actual fraudulent transactions, we might give up a little bit of overall accuracy to increase the fraudulent accuracy. So yeah, there's free stuff in here. There's free trial stuff in here. There's subscription models in here. There's pay-per-use models, all kinds of things. So I'm using the word models there. I shouldn't use the word model. I mean, methods, right? Like not talking about machine learning models in that case, right? Different ways to pay for things. All right. Okay. So we talked about these already. So just to kind of highlight these parameters, these are learned and updated during training. So when a training process is happening, parameters are being adjusted. Okay. They're tuned automatically by the model during the training process. And some examples of parameters, there's not very many, weights and bias. Okay. So we make these are variables basically that get adjusted during the learning process. Okay. So those are not controlled by us directly. Indirectly, they're controlled by us by we tell them how to make their adjustments, right? So through a hyperparameter, we're going to say, hey, here's my loss function. I want to use mini batch gradient descent. That's my loss function. I want to have a batch size of 200, and I want the learning rate to be X. And so that's kind of the size of the learning rate overall. And then, of course, stochastic or of course, gradient descent can make adjustments to it. But so these are all things that are going to be fed in as settings to and then the parameters are going to use these, right? So again, the weight is going to be adjusted by what value? Well, that's going to be determined by the learning rate, loss function, and batch size, perhaps, right? So all those things. So, and then weight initializations, right? That's what I was talking about, the starting point, okay? And then hyperparameter tuning. So adjusting all of these things is the hardest part of this. All of this that we're talking about, the hardest part is actually coming up with the right values, okay? So what is the right learning rate? What is the right loss function? What is the right batch size? And there's a whole bunch of others that we could choose. These are just some examples. There are lots of hyperparameters. And what are the right hyperparameters? That's the hardest part. It's a guess on our part a lot of times, where we might guess a learning rate, produce a model, adjust the learning rate, produce another model, and see which one produced a better model. Right? So it's a guess. It's an educated guess. Fortunately, SageMaker has a wonderful feature called automatic hyperparameter tuning. It'll actually help you pick the right values for these hyperparameters. This is huge, because without that, it's just a guess. It's still going to be a level of a guess. It's not going to be perfect, but the system will get you pretty darn close. And I'll show you that. I'll demonstrate that later. Okay, I think that'll be a demonstration probably for tomorrow, I think. It might be today. We'll see. So creating a training job, SageMaker. We have our training image. Okay. Again, that is our algorithms and frameworks and things like that. We have our training data. Neither one of these actually sit in the training systems, right? They are pulled in. Okay. They are pulled in to the system and then run. This is, again, one of the elegant aspects of SageMaker is, as we talked about, you could swap out your image for something else. Your data can be whatever you need it to be. Just have it sitting on S3, and off you go. All right. It can also sit on something like the different storage options we talked about, right? But it's going to get pulled in at the time a training activity is initiated. And so this all comes online at the time we initiate a training job. And then this stuff is pulled in dynamically. And then when it's all done, it produces a model, puts that model back on S3, and the whole environment gets destroyed every single time. So if I want to produce 10 models, I can do them all at the same time. And each model is being produced in its own separate, isolated environment. So whether I create 10 models at once, or one model, or 100 models, it doesn't matter. It's the same amount of time. Same amount of time to produce 100 models at one time as it is to produce one model at one time, because it's all in parallel, right? Each model gets its own dedicated, its own environment for that moment in time during the training process, and then it all goes away. Okay, there's no bottlenecks that'll ever occur here. Okay. Here's a PCA algorithm example. Now, I mentioned PCA before. We're not really going to talk about it. This is just some code examples here, where we're showing you setting some hyperparameters. Okay, so here's the thing. Kind of walk you through this lightly. You're gonna continuously do this quite a bit throughout the class as you do your training jobs. We're going to see we have what we call this estimator, and an estimator is the hardware that we're going to use. We're going to build the hardware here. Now, specifying the estimator here does not build the hardware yet. It's really just setting the specifications for the hardware. So, how many nodes do we want to train on? Do we want just a single training instance, or do we want multiple? Multiple, little note on that, multiple will not do you any good if it's not an algorithm that can be a distributed training process. Okay, keep that in mind. If we tell it, hey, I want it to train on 10 instances, that's pointless if the algorithm doesn't have the ability of distributing its training logic across 10 instances. So it's only going to use one, but you'll pay for 10. Okay. The training instance type, again, goes back to that family and size and all of that. Your output path, this is basically where is it going to save the model. Okay. And then we have our hyperparameters that are being fed in here. Okay. And then we have this fit command. PCA.fit is when the training activity actually begins. Okay. And at this moment, we say PCA.fit or just .fit. It doesn't have to be PCA. Just the .fit function is ultimately going to tell SageMaker, this is coming from the SageMaker SDK up here. Okay. The SageMaker SDK has the .fit. And so .fit kicks off the process with SageMaker. And you notice here, I'm telling SageMaker, I'm going to tell it where the data resides as part of the fit command. I'm going to tell it, hey, here's where the data sits. And it's not going to be, I don't really want it to be local on my machine. I mean, in all reality, this should be sitting over on S3 so that it's all dynamic. Okay. It has nothing to do with the notebook instance at that point. Okay. Or wherever you're doing this. Okay. Okay. So Jeffrey, containers are not defined unless you're doing custom stuff because those are already built in. Okay. If you're doing custom stuff and you want to define these containers, so I'm guessing you're kind of talking about, if I'm doing some of this stuff, there's going to be extra code for that where we're going to tell it where to find the container. The container will be stored in ECR, and there's going to be a URL for that ECR container, that image, and you would specify that in your script as well. But because this example is just referencing the built-in, you never have to define the containers. The containers are already predefined. Okay, you only define the containers if you're doing something custom. Otherwise, containers are irrelevant. We need to know how the process works and how it's built architecturally, but the containers have no bearing on anything we do unless we're choosing to go custom stuff. Okay, so just to clarify that. Otherwise, you just specify the containers in your code as well. All it's going to be is, we're not defining this yet. At this point, we don't need to define it. Okay, that's why it's not here, Jeffrey. So go look at the documentation on how to do this custom. You can walk through that. It's very clearly walked through in the documentation. It'll show you how to do that. It's not going to be quote unquote containers, but it's not going to be a variable. We don't need to worry about that variable right now because it's irrelevant to it right now. Okay, it's only relevant if we're doing something custom. If we're doing something custom, there will be a couple of other commands you're going to have to include in here as part of your estimator. Okay. And then, no errors at all. So Jeffrey, I'm not quite sure. Again, the containers are part of the service. Okay.
He's saying as an argument to the estimator, there's a list called containers, or maybe a deck, I don't know. There's a variable called containers. And
but we don't have to specify it. It's predefined.
Right. So is that something that's defined in the Amazon and the AWS SDK or in the SageMaker SDK? In one of the
No, it's none of it. So I mean, so I want to clarify. SageMaker is a service. All you have to do is tell SageMaker go train, and you tell it where the data is, and you tell it where your outputs are, and it just does it. That's the beauty of a service, right? The service already knows where its own containers live.
So I think Jeffrey's talking about in the code you showed us specifically, it references a variable that doesn't seem to be defined elsewhere. So in PCA equals SageMaker, estimator, and that first argument, containers, it's it looks like
I see what you're saying. Yeah, that's the optional. So because I see what you're getting at. Okay.
And that doesn't seem to be actually defined anywhere in this.
It'll pull in the defaults if you don't define it. It's just a default on the back end. Yeah. I actually wasn't cluing into that. Thank you for clarifying that though. So I don't believe this will throw an error because it's not defined. And so it uses the defaults. And I believe in the case, I do believe the SDK is handling that for you. But yeah, I would just look at the documentation and if you need to use the containers, but you don't have to specify containers. You really shouldn't specify them unless you're doing custom work. But I see what you're saying. Yeah. Okay. Sorry. My apologies. I wasn't cluing into that. So the right here, containers is specified, and that's what was being kind of brought up. The SDK handles a lot of stuff behind the scenes for you. A lot of your defaults and things like that are just handled. But the service itself also handles a lot of things you don't even have to define even through the SDK. This one, I would have to check on that as far as, I don't even think this should be there, to be honest. So yeah, in that case, this is probably an error in the code. Or it may just be optionally fed in. I would have to dig into that one a little bit more. But bottom line, you don't need to specify containers at all.
Thank you.
So it could be an error. I'd have to play with that. So it's very possible this could throw an error to that point. That was brought up earlier. It could. I don't know. I'd have to play around with it. I don't usually see containers even specified there. So this slide may be a little bit troublesome. I'll have to play around with that and see. Thanks for bringing that up. So let's just go ahead and create a training job, and then we're going to kind of look at some of the logs and stuff as well. So we've got this demo, creating a SageMaker training job. I'm going to go ahead and walk you through doing this. All right. So what I'm going to do here is show you how to make a training job in the web console. Okay. The reason we like to do it in the web console is visually, it's kind of just a little bit easier to grasp. And then when you go to do it, you're going to do it in the code. So you can kind of envision what you're doing with the code at that point. It's the same thing either way. One thing for those of you that aren't overly versed in AWS, just know the web console has no special hooks into AWS. It's just making API calls on our behalf. So there is not a single drop down or a single field anywhere in the web console that I couldn't simultaneously automate. I could automate them with a CLI. I could automate them with the SDKs. I could automate them with just raw REST API calls. Okay, it's all at the end of the day coming down to an API call. And so the web console makes that API call for you. So whether it's the web console, the CLI, or the SDK, it's all the same thing. Okay. It's just this is more visual versus the code. You're actually making the calls to the SDK, but the SDK is then converting those and actually handling those with the raw REST API calls as well. Okay. Oh, containers. No, containers don't need to be imported at all. The SDK is all you need there. So to one final answer on that one for Jeffrey there. Yeah, the SDK, the SageMaker is already being imported and it's got everything you need there. Yeah. And you're just specifying, you're telling SageMaker how to do what it does, but you're not actually doing it. So you don't have to write all the logic. That's the beauty of it, is between the SDK and the SageMaker service, it does everything for you. You just simply give it the instructions. That's all you're doing. But you're not having to make all the complex logic code and all of that. And there's no imports or anything. It's part of the SageMaker SDK. Yeah. Okay. So let's go ahead and look at the training jobs here. Okay, so first off, under training, you have algorithms here. I want to kind of show you a little bit on the dashboard here what we're looking at. This is where I could find algorithms. Remember that marketplace we were talking about? If I came in here, I could find all kinds of commercial stuff and whatnot. And I mean, there's a lot of things that I could dig into here. Some anomaly detection stuff, some image recognition stuff made by these third parties. So you see there's a free trial here. TIBCO, hospital stuff here, predict hospital readmissions. That's interesting, right? So there's some pretty cool stuff in here. So you could just go grab these. And again, these are just containers at that point that are provided by that vendor. And you can pull those in. Now, of course, just like any vendor, you're going to have some stuff that's maybe not as good as others. This is only one review, so 2 stars. Who knows if it's good or not off of one review? But and a lot of these, there's 24 external reviews. Some of these are not even reviewed at all. I think a lot of people don't take the time to review these things. They just use them, and they like them or not, and then that's that. But I don't even think a lot of people realize they can review them. But if you do, it helps others, right? But ultimately, this is where your marketplace kind of sits. Go back to. Can I get back? Come on. Let me make sure. Maybe I just open a new window. No. All right. Let me see. I got to get back to. Somehow I'm stuck in here. Let me go back to my main menu here, my main window. What happened there? That was kind of weird. And it was my browser issue of some sort. Normally the back button works just fine on that, but it's kind of weird. So on that note, actually a better practice, real quick note on that when you're working through the browser stuff here. I didn't do it this time. But if you're opening up some other window like this, I mean, it shows like a little arrow, like it's going to be call out. I usually like to right click and open in a new window or new tab or something, just so that I don't have to hit back and do all of that. I just didn't do that this time, but normally that's what I do. And you can also create an algorithm. And if I create an algorithm, look at this. I can actually specify my images and stuff here, right? So stored as a Docker container in ECR, I give it that, and then I can reference this in my code, of course, or I can reference this when I go to actually select my algorithm when I'm building out my training job. Okay. All right. So we're not going to do algorithms right now. We're just going to do a training job. Now, I already did this. Now, I use this account for a lot of my demos and stuff. I did an ML pipeline class back in November, and so that was some stuff from that. So this is one I just did this morning while you were all doing one of your checkpoint. When you're doing that checkpoint, actually, I did this training job here. So I'm going to do the same training job and walk you through it, but we're not going to have to wait for it to finish because I already did it. So while it's going, we'll look at the outcome of this. Okay, so I'm going to do the exact same settings, but we're going to create another one here. So what I'm going to do is create training job. We're going to give it a name, but what I'm going to do is okay, like that, just so I you tell the difference between the two. Okay, so I'm going to give it a training job. I'm going to give it a name for the training job. The role is the permissions that I'm giving the training job, which is going to run on some virtual machines. Those virtual machines need permissions to places like S3 and things like that to be able to retrieve the data and also write the results. So there's some permissions I already have set up here for that. And then I'm just going to use right here, you see built-in algorithm, or use your own algorithm, use your own container, right? And so there's a lot of options here. Built in, like I said, is most of the time going to be what you need it to be. My algorithm, I'm going to go ahead and use what we call linear learner. We're not going to try and explain the algorithm in too much detail here. That's not the goal of what we're doing here. I'm just picking an algorithm right now and just going to run with it. I'm trying to show you more about the training job aspect of SageMaker, less about the algorithm, okay? But, and then there's this input mode file. You see this pipe and file. We'll talk about that in a minute here. You could change this right here, but all that does is kind of acts as like a global setting. I'm going to actually set the setting on in another place in more specific details. So this is really not all that important unless I just want to make a global setting for the whole training job. And then you see right here, these metrics. This question was asked before as far as what we might consider an important piece for what we consider good, right? So like, how do we know what we're looking for? What is the important part here? So you see here, there's these metric names. So precision, recall, AUC score. These are all scores and ways to understand what we consider good about the model. Okay. So we can utilize these. These are metrics that are published through the monitoring process of the training job. And so when it's done, it'll produce these values for me, and I can use those in my own evaluation of the model. Okay. So these are all provided as metrics, all of them. So I perform the training job. All these metrics are going to be things that I can look at. Okay. Resource configuration. This is my estimator right here. I know it's labeled a little differently. I kind of wish they used the same vernacular in the code as they do in the website and the web console, but they don't. So the instance type I'm going to use, I'm just going to use an ML M4 extra large for this example. No problem there. I'm only going to use one instance. Again, if I did 10 instances here, you would think, oh, is that going to go 10 times faster? Actually, not at all. All I'm going to do is increase my costs by 10-fold, and I'm not going to get any benefit out of it. Why? Because linear learner does not have the capability of working across more than one instance. That's a limitation of the algorithm. It is not a distributed algorithm, and I highlighted that word distributed. Distributed is a very important word because the algorithm would need the ability to be able to work across instances and have it, split up its workload and coordinate that workload across 10 nodes. That is a very complicated job or complicated task. A lot of your algorithms don't do that. Okay, so just adding instances here doesn't necessarily help you. Now, keep in mind, I could create 10 models at the same time. Each one gets a single instance, and I would be creating 10 separate models. But I'm not going to be able to create one model with multiple instances unless the algorithm is capable of it. Okay, that's very important. And then storage, how much storage does each instance maybe need? If we are doing some custom scripts or some certain work, maybe it needs some local storage. We're not going to really do that here. It's kind of leaving the defaults in play. Maximum runtime. So maybe I don't want this training job to just get stuck and run indefinitely. I need to have a hard cut. This training job should run no more than 5 minutes. So I'm just going to put a maximum runtime, knowing that it's a short one. I'm going to say maximum runtime is 15 minutes. After 15 minutes, if it's not done, it's just going to kill the process. Okay. If I want to end a specific network, I could do that. I'm not going to bother with that right now. And then here are your hyperparameters. So these hyperparameters come in from the algorithm. Okay. These are inputs. These are runtime inputs that the algorithm allows for me to specify. So one thing you'll notice about SageMaker, this is one of those areas where it's not overly clean looking, and it's by design. So you look at this, like they're not into alphabetical order. They seem to be kind of all over the place, as these are all hyperparameters, by the way, for linear learner. Okay. Now, the reason they're kind of all over the place, not in alphabetical order and stuff, is SageMaker doesn't do anything with these. These are simply brought in from the algorithm. So if the algorithm displays them this way, this is what we see. Okay. And again, that's by design, because the whole point is that we should be able to have any algorithm we want here, and we can still specify our hyperparameters. So SageMaker really doesn't know about these. It doesn't need to know about these. These are just inputs into the algorithm. SageMaker is simply running a container as far as it's concerned. Okay, so I'm going to put some values in here. We don't need to explain the exact values, but for linear learner, I'm going to give it a feature dimension of 64. And the predictor type is we're going to do a multi-class classifier. And we're going to say we have 10 classes. So I have some classes down here. I'm going to do number of classes 10. And again, the point of this, I don't want to get hung up on these hyperparameters right now. So I'm not going to explain any of those. Okay, so we have this training channel. We're going to specify my training data. We're going to tell it where to get my training data from. Okay, keep in mind, we already did some pre-processing. So the demo I'm doing here, I've already done the pre-processing, and I've got a training file, and I've got a validation file, and I've got a test file. And they're just very simple CSVs, nothing too crazy. I have train data, validation data, and test data already split up. You do that in your code, but in this case, I've already kind of stepped ahead, and I've already got that data as separate CSVs in this case. Okay. So the training mode, there's pipe and file. Now let me explain the differences between the two of these. File will treat this as a file. So what will happen is I will tell it, I'm going to come down here and I'm going to give it a location of my data, and it will have to copy the file. So the file from S3 will be pulled into the system entirely before it starts processing it. And there's some variations there on how we handle that in memory versus on disk and all that, but that's another discussion. The point is it has to copy, it has to bring all of the data in before it can actually do anything with it. One of the really nice things about an object store like S3 is there's things you can do with object stores that you really can't do with a file store, which you can't do with a file system. S3 is not a file system. It is an object store. And because of that, I can actually stream the data. And what we're doing here is the first byte it receives from that stream, from that pipe, it's actually able to pipe the data into the system. And as you're receiving the data, it's able to start processing, starting with that very first byte. So we don't have to wait for the data to copy first. As soon as it starts receiving the data, it can start going. And so this speeds up that initial starting point, okay? and it'll start processing as soon as it possibly can. So this usually makes things a little bit faster when we're using S3 as a data source. We can go ahead and pipe it. There's not really much in the way of negatives to this. There's really only positives, but you can't do pipe for non-object stores. I mean, it's got to be an object store for it. Okay. All right. It's a CSV. We're just going to tell it that. It's optional, but still good to specify it. If you don't specify it, I believe it defaults to CSV. But here's where, remember we talked about you could specify a record IO protobuf or things like that. So you could specify that content type here as well. And the data source is an S3. And I've got a location over here I'm just going to copy and paste from. Right. And we're going to add a channel. Now, these channels are really nothing more than multiple data sources. They're input data sources. The first one is a train channel, right? And then I'm also going to have a validation channel, okay? And it's called validation, okay? The reason I'm highlighting this or trying to tell you, look, it's called validation. When it was tested, it said it was duplicate. I changed the name and we're good to go. Now, I've messed up on these demos before, and I did like that, validate. That won't work. It needs to be validation. And how do I know what that is? If you go look in the documentation for Linear Learner, it's expecting this phrase. Okay, this is a keyword it needs to know. It needs to know that this is validation data that we're specifying. So when it comes to your channel selections here, you have to know what is expected as the channel name. This isn't something you just make up. Okay, it has to be whatever the algorithm supports. So you got to go look in the algorithm documentation to know what's expected here. And that's why it's not a drop down or something. I have to type it in because, again, each algorithm is completely different. So these are some of the small drawbacks, very minor, but small drawbacks of it being as dynamic as it is, because if it was hard coded, if SageMaker said, here are the 17 algorithms you can use, period, with no ability to do anything custom, they could make all these drop downs. But they've made the system to be very dynamic. And because of that, these aren't drop downs. These are fields that are inputs to the algorithms. You need to know what's expected here. Okay. So great question, Jeffrey, about kind of how chunks of data as opposed to, how that it kind of correlates, if you will. I'm kind of just summarizing here in my own terms, how it kind of correlates to piping and streaming the data. Well, it doesn't matter. So the nice thing here is this doesn't actually have much to do with the algorithm per se, because think about how the system would read the data into its memory, as an example, off of disk. It's loading the data. It's basically starting at the top and working its way to the bottom until it's all in memory. Even if it happens seemingly instantaneously, it's starting at the very beginning and it's loading it in, right? So the pipe presents it to the system the same way, and it's just going to start going through the records, loading them into memory, pulling them in as they're coming in. Okay. So it just may be not as fast as if it were truly local, but the behavior to the system looks the same. Okay. It's like it's reading the file, and when it's reading the file, it's going to start with, row 1 and go to the end. Right. So the stream allows you to do that without having the OS files be a problem, because normally a partial file would be a corrupt file. And in the case of a stream, an object can actually be read that way. You can actually read byte ranges from an object. And so it's able to be streamed differently than a file can. And so, but at the end of the day, the OS sees it as a file. The OS still is loading and reading that data in the exact same way. So this actually is not algorithm specific. It doesn't have anything to do with gradient descent or stochastic gradient descent or mini batch gradient descent or any of those kind of things either. Okay, it has nothing to do with any of that. It has to do with just how it's getting the data into the system, into memory, and how quickly it's able to start its process. Okay. Yeah. No, it doesn't have to finish. That's just to clarify. It does not have to finish streaming, because no algorithms read all of the data at once. They're still going to read the data from row 1 to row 5,000, right? They're going to start at the top and work to the bottom as it reads. Even if it's very, very quick, that's how it's going to read the data, right? So that's what happens on a stream. It's just able to start as soon as it has row 1 available. It's able to see row 1 and starts working with it, and then it's going to read row 2 and read row 3, read row 4, read row 5. As it's coming in, it's reading that. It's reading it like it's reading it naturally locally instead. It's just maybe not going to be as fast. Locally, it won't be as fast, but you don't have to wait for the copy to finish before it starts. So although it's technically going to be a little bit slower to get it up into that memory, technically speaking, because the net process is faster, you're going to end up with a faster result, even though you're more network dependent at that point as far as how fast the network's able to get it into the memory there, right? But at the end of the day, yeah, it's just reading the file. As far as the OS is concerned, as far as the framework is concerned, as far as the algorithm is concerned, it's just reading the file from top down. Okay, it's able to start reading it immediately as it's streaming in. Yeah. It's an interesting concept. And it requires to really, really kind of grasp this, though, of what's really going on. It does require a pretty deep, advanced knowledge of object stores and how all of this stuff works. Definitely beyond the scope of this class and the exam, but just kind of understanding how those things actually work. There's a lot more we could get into in the background of how object stores read, how you can read data from object stores. But as far as the OS is concerned, it doesn't see it any differently. It just thinks it's opening a file. It's just that the file isn't all there yet. And as the file becomes, as those records become available, as they come in, it's reading them. It just may take a little longer to read them locally, but you don't have to wait for the file to get copied first. Yeah. Okay, good. Awesome. Great questions. Questions I don't usually get. So I like the way y'all are thinking. You're thinking in terms of that you really need to be thinking. How is this really working behind the scenes? And that's really important because it helps you understand the bigger picture. Okay. Okay, so a great question, Jennifer. So to clarify on this has nothing to do with SageMaker. These channel names are specific to the algorithm chosen, which would be the same whether you're in SageMaker, whether you're doing this on premises, whether you're doing this in Google, it doesn't matter. Linear Learner supports train channel. It supports a validation channel name, and it supports a test channel name. That's what Linear Learner supports. So the reason I would get an error here is not because of SageMaker, it's because of the algorithm. And then that goes back full circle what I was talking about, like drop downs. The reason you have to type it in is because SageMaker doesn't even know about this. The algorithm is expecting it. So whatever you put in here, SageMaker passes to the algorithm, and the algorithm will give you an error because it's an invalid input. So the reason SageMaker doesn't make this easier for you, if it was just a nice drop down, it would look a lot cleaner, but the reason it's not is because every algorithm has its own inputs. Yep, exactly. So I showed you that earlier, right, Alexander? So we showed you that. I don't know if you missed that or not, where I showed you there was all that algorithm documentation. I only showed you the place that was more about selecting your algorithm. But on the left-hand side there, if you recall, I was showing you all the algorithms are there. And each algorithm has its own documentation, and you can go into that and it'll show you your inputs and your outputs and all kinds of hyperparameter documentation and stuff about that algorithm. Okay. So each and every algorithm is documented. Here's the thing. You don't even need to go to the SageMaker documentation for that, though. If you go on the industry, just regular internet search, right? And just do a search for Linear Learner input channels or just inputs or Linear Learner documentation, you're going to find public documentation on Linear Learner that will tell you what the input channels are that's supported there. Okay. So yes, SageMaker provides you that information, but it is actually not SageMaker documentation. It is linear learner documentation in all reality. The SageMaker documentation gives you a bit more because it's also going to kind of talk about the SageMaker interaction. In that, so that's why Amazon does provide that additional documentation, right? But remember SageMaker algorithms? We looked at this earlier. So choosing an algorithm, okay, built-in algorithms, we got all these. Let's go to linear learner, and it explains all of how it works. Input, output, okay, tells you different file types that you can use, things like that. Also, it's going to talk about hyperparameters that are specific to linear learner. Again, the hyperparameters are not a SageMaker thing. The hyperparameters are an algorithm thing. Okay, so linear learner, whether you use it in AWS or not, linear learner is linear learner. It is a public, well-known, industry-used algorithm, and these are the hyperparameters that it can use. Okay, and it goes through and explains what each one does. Okay. And so like I did feature dimensions, right? Number of features of the input data. Also, you could do like auto or something there. I put 64. I don't think we actually have 64 dimensions. I think that's just so that the data can be kind of up to that amount or whatever. But you know, you could go through here and learn about each and every hyperparameter. I wish I wouldn't say parameter name here. I wish it would say hyperparameter because these are not parameters. But you get the idea. Hopefully, all the documentation here. And so, you know, your inputs, as I mentioned, I mean, I didn't go through it all here, but it should be in here. Oops, linear learner. Let me back up. May not be called channel. Yeah, here we go, right here. So the inputs, outputs, right here, supports 3 data channels: train, validation, and test. Validation and test are technically optional. All you need at minimum is train, but there you go. Okay. Yep, exactly, Jeffrey. Yeah, I think I've covered a lot with you, so I have no problem going over things multiple times. We have to because you're not gonna catch it all. But yeah, that's what I was saying. There's not a single thing in the web console we can't automate. 100% of this is automatable. If you remember, I was talking about like the web console, the CLI, the SDKs. They're all just wrappers for the APIs. So when you're using the SageMaker API, all of this stuff is there, all of it. 100% yes. Yeah, exactly. Yeah, and I have no problem. So ask those questions. Keep digging in because we need that clarification. I don't want any vagueness out there. I don't want any misunderstandings. Or sometimes I speak quickly, and I may kind of just fly through something too. So definitely keep clarifying, keep going. Okay, so so we did a train channel here, and we're piping it, and I gave it a location for my training data. I want to also do validation. It's also a text CSV, and then we're going to do the source. I also have validation data that I can use here, and I'm going to give it the location of that in my S3 bucket here. And we're just going to do this 2 channels. I'm not going to bother with test right now. This is just to produce the model. The test, a test channel would actually then perform an additional test once the model's done. We're just trying to show creation of the model right now, but that would just be another channel, and it wouldn't really be too much more. It would just go through more activities than it needs to. And then you could do checkpoints if you needed to. I'm going to skip that, but you could do checkpoints so that it can kind of save its work as it goes. So if there were ever like something failed along the way, it could actually pick up where it left off if you had checkpoints. Output data. So this is where it's going to store the model. Okay. So I've got a bucket I've set up for my outputs. I created a new bucket for classes this year. I had another one that was an output bucket for 2021. I've got a ton of models in there from all my demos. I got to delete them one of these days, but the models are small, so they're not really doing much, not costing me much, a couple pennies. So I'm going to go ahead and create this training job. So I told it where to put the model, right, in that last step. So this is running. Okay. Now, like I said, I already did this. All those same settings I already did. So we're going to come in and look at this one. So I want to show you a couple things. You know, if I click into it, it's going to show me a couple things. The training time. Okay. I want to back up real quick before I go any farther. The duration of my training job took 5 minutes right here. Okay. I I don't pay for 5 minutes. That's what's really cool here. Is this includes the building of the training server, if you will, the virtual machine that is being used here is getting built and coming online. I don't pay for any of that time. It's only the actual training process. So as training kicks off, when the training activity begins, then the billing starts billing. Okay. And then when the training ends, I don't have to wait for the system to be destroyed for billing to stop. It is going to be destroyed, but I don't pay for that time. I only pay for the actual training time. This is really cool because I only had to pay for 115 seconds of training time. Okay. Something else, you'll notice billable time and training time look the same here. Okay. The reason why these are two different values and they may differ, what if I was doing a distributed training job with a different algorithm that supported it, and I had 10 training instances running at the same time. The training time may be 115 seconds, but it was 115 seconds times 10 instances. My billable time in that case would actually be 1,115 billable seconds. Okay, does that make sense? So because it's only a single instance, these will match. But as soon as I do parallel instances, the training time is the actual like clock time that it took. But that's across 10 nodes. It's actually going to be 10 times that. So the billable time would be different than training time in that situation. Okay. This tells me what permissions were being used for it. It shows me some details about what we set up. Remember, now in this one, I forgot to change the maximum runtime. I left it at 24 hours. But that's the only difference between the two. But otherwise, the instance type, instance count, input mode was pipe. We see all the stuff that we set, right? So this should all match everything that we just did. The hyperparameters, again, I changed this feature dimension to 64. I changed it to a multi-class classifier with 10 classes. Okay. Yep. .fit does exactly this. Yeah. .fit does it all. So the .fit kicks this whole process off using your estimator and all of those other things that you've defined in your code. Yeah, great question. Yep. So .fit is like the same as me clicking the button where I said go train. You know, .fit does that. Okay. And so this is just all stuff about my model. Now this model didn't run long enough to really get, I didn't make a bunch of adjustments on my monitoring. So like some of these values, it would need to run, I would need to have a training job run for like probably 20 minutes or so to really get any real valuable data here, because these data points are pulled in on intervals. It will show you all of the historical data, but it's on intervals. So this didn't run long enough to really generate any real, measurements here. Now I could change the metrics around to actually be able to see it, but it's basically too small of an increment to really be able to see what happened there. I mean, you see, I could go really, really big here on, how far back, but let's I didn't do anything with the monitoring. So those are all kind of vague. But then the output is stored over in this bucket right here. So this tells me where the model artifact is stored. Okay, opened a new tab. Thank goodness. I realized I forgot to do that. So here is my training bucket, this bucket right here I created. And I want to go back to the root of the bucket. It automatically names the prefix with the name of the job. Okay, so I go into the name of the job, and then I see the output, and I've got this this model sitting here. Okay, now because I have another one running right now, let's just see if that job is about done. It's still running. It's probably going to be done here any minute. When it does finish, I'll see that show up back here at the root right here. I'm sure if I refresh this in a minute or two, it'll probably be there. That's the model. Okay. Now let's look at some other things about this model that was already done. View history. If I look at the history of this, this is the high level history. This is not the full logs. Okay. This just kind of shows you the major events that occurred for the training job. So it prepared the instances for training. It downloaded the input data. The training image was downloaded. Okay. And then training in progress at that point. Image was downloaded and then started using it. And then when it was done, it uploaded the trained model, and then it completed the job and ultimately destroyed the resources at that point. Okay. So those are the main events that occurred. Now, what if I want to look at the logs for this training job, the actual logs for it? I want to see every little thing that occurred. So here's what's kind of cool. I don't think there's a link for it in here. I just wanted to see if there was. I couldn't remember. I'm just trying to see if we've got the link to the logs. Whoops. We don't. Okay. So what you're going to do to get to the logs is you're going to go to CloudWatch. I'm going to open this in a new tab. Close that. Okay. So I've got CloudWatch opened up. CloudWatch is a monitoring tool in AWS. It collects metrics. It also collects logs. So it's got a logs component here. If I go into the logs here and I look at my log groups, I should see a log group for the training job. And so right here, SageMaker training jobs. And if I go into that, I'm going to see these different streams. Each training job actually has its own log stream. All right. So let's see here. I just have it sorted here. See last event time. There we go. Okay. So this was the one that I did before class. And this is the one that's going on right now, unless it's finished. But that's that live demo one I did, right? So we could look at either one of these. And if we go into it, you'll actually see every single output, every single thing that happened during this training process, right? So if we look at these things, look at this, Epoch 13 loss improved. Okay, updating best model. All right. So you'll actually see these metrics and the values it's coming up with. The algorithm is actually running, right? And you're actually able to see what it's doing all along the way here. You see right here, entropy objective. We've got these minimums and maximums, all these things, these metrics that are being tweaked each time, right? So quality metric right here, we have, every little thing that's happening, in the training job is all right here. Okay. Saving model for Epoch 14. Okay. And it keeps going through its epochs, validation score, right? It's looking at some of these things. Right. And it's going through. And at the very end, test data is not provided. So it just stated that. Best model found for hyperparameters or whatever, so it's got this best model basically that it found in all reality. Okay. So we're going to look at these a little bit more detail later on. We're going to actually do some things like hyperparameter tuning and stuff. And this all starts to get a little deeper as well. So anyways, let's go take a look. I think the training job that we kicked off has got to be done by now. Yep. So for some reason, this one took 6 minutes this time. Don't know why. Maybe the instance took a little longer to come online or something. Who knows? Maybe this was just on the edge. See, it's rounded. So it could have been like 5 minutes and 55 seconds. And maybe this one was 6 minutes and 1 second for all I know. Right. But basically you can come in here and again, we should see all the same stuff. And again, your output, if I go back to the S3 bucket here, if I refresh to this, go into my bucket here. I could have hit the refresh button, but I just kind of, I'll go figure it didn't refresh. Let's see, refresh. There we go. So now it's there. So sometimes you have to refresh your browser. There's big reasons behind that. I'm not going to get into because browser refreshes aren't forced a lot of times because each time I refresh this browser, it's issuing a ton of API calls. And so instead of Amazon just
bombarding itself with a bunch of API calls. It kind of waits for you a lot of times to update the browser. So just keep that in mind. Okay. So I go into this and we see the output model we just created. Okay. So that was it. It took, 5-6 minutes for a model to run. Billable model time on that was very, very small. Let me just show you real quick. We'll let you go to break or to lunch, but let me show you one final thing. I want to talk about costs of this. How much did this training job actually cost us? Well, I kind of wish it just said it right in here. So this one took 115 seconds to train. Let me look at the other one that we just did. This one says 6 minutes duration, but actually look at this. The training time was less. I don't know why sometimes these variations, behind the scenes, it's selecting the best hardware. Maybe there's different zones that it's using and, other things. So there's a lot of factors here, but this one only charged me 78 seconds to train, 78 seconds. So how much does that cost me? Well, it's how can we figure that out? It is an ML M4 extra large instance for training. So if we go SageMaker pricing, let me try refreshing that again. That didn't load, right? Okay, there we go. No, you're not going to go through this as part of the lab. So I am showing you in the web console, you're going to do this stuff in the lab, not for pricing. You're going to do so you are going to do training in the lab, yes, but you're going to do training via the code. Okay. So Alexander, yes and no. Okay. You're going to go do your own training jobs. I just wanted to walk through all the little intricate, some of the details and discussion topics visually, and then you're going to go run through that stuff in your code. And that way it kind of helps connect the dots a little bit. When you do the stuff in the code in the lab, it's sometimes helpful to kind of see it in a more visual way, kind of the web console, and kind of understand how your code is connecting, right? How that's kind of connect the dots there, right? Okay, so let's look at prices real quick of that training job. So this is training. Okay, so the SageMaker service did the training job, not the notebook. Okay, keep that in mind. And a lot of times you'll see this happen while it's loading. What it's doing is actually making live API requests for live pricing. Billing and pricing are API calls as well. Everything is an API call in AWS. And so these prices are not just statically on some page somewhere, although I think there may be something stuck. So let me just do a refresh. I'm going to go to training. It's probably on my browser side, I'm guessing. Especially since like I said, since I updated from Windows 10 to Windows 11, my performance has gone in the tank. Okay, so let's see. ML M4 extra large. ML M4 extra large. So this is the instance that we used. 24 cents per hour. So let's see how much this training job cost us to run. I'm going to open up a calculator. Okay. So 0.24 cents per hour divided by 60 minutes in an hour divided by 60 seconds. I guess I could have done it with the, 3,600 seconds in an hour, right? So let me just do that just to verify. So 24 divided by 3,600. Yeah. Okay. Same answer. Okay. So that's how much it is per second. And the job was 78 seconds, right? 78 seconds. So multiply that by 78. And I paid half a penny. All right. Half a penny for that model. Isn't that pretty cool? This is one of the reasons why we use SageMaker to do training jobs. All right. You only pay for the training job. You only pay for the time it's training, I should say, not even the instances and the duration. You pay for the training time. Okay. Cost me half a penny. Do you think a small mom and pop company that doesn't afford a lot of resources could do machine learning now. Companies that previously didn't have the investment capital to build machine learning environments, now it's fully accessible to everybody, right? I've done a bunch of machine learning for some local nonprofits where they needed some. I felt they needed some help on managing some of their resources better, and so they were doing some marketing, and they were just blanketing the environment, the area with mailers. Of course, 90% of us just throw them away. So we were able to do more targeted marketing and stuff with them, just doing some machine learning, algorithms, some models, I should say. So, it's accessible. And at that point I was like, don't worry about it. I got it covered. I don't have to bill them for it because, the work on my part was time, but the actual resource costs for like this bunch of stuff we did for them, my costs out of pocket were probably like less than $2, when all said and done. So there was no reason for me to bill them at all for it. It was just volunteer work that I was helping them with. So, it's pretty cool when, I can create a model for half a penny, Okay. So, anyways, I'm gonna let you get to lunch. I think that's probably good enough for now. When we get back from lunch, we'll do another checkpoint, just to kind of see how we're doing on all of this. And then we'll talk about model evaluation, and we'll get you into lab 3. And then kind of like yesterday, lab 3 is pretty much going to take us through a good chunk of the afternoon. And then we'll be getting through. The lab 3 is going to consist of you training your model and also evaluating it. Okay. So in other words, how good was the model, and could you adjust some things like hyperparameters and stuff to make it better? What are things that you could do to improve it? So that's what we're going to do today. So today in your project, you are going to create your model, and you're going to take a look at it and evaluate its quality. Okay. Its performance. All right. So we are at 12:26 Eastern time. So maybe we just make it even numbers. We'll call it 12:30. It's only a couple minutes shy of that. And so we'll come back at 1:30. Okay. You get a full hour. Try and not let that full hour go to waste. Make sure you use it to get caught up on any work so that you can focus this afternoon and really work on your labs and stuff. Okay. All right, everybody. We'll see you back here 1:30 Eastern. All right. Have a great lunch. All right, go ahead and mark that green check if you would. Let me know you're back and ready to go. All right, just one moment here. Stay for just a second here, just making some small things happen on my end. Just 1 second. All right, so welcome back from lunch. So we're going to go ahead and do a quick evaluation here. Another one of those kind of checkpoints along the way here. Let me give you the checkpoint link in the chat. And just like before, maybe take about 10 minutes or less, go over this. Go ahead and use the green check to let me know when you're done going through it, and then we'll talk about it. All right. I'll give you about 10 minutes or less, just kind of see how everybody's doing. When you're done, go ahead and mark that you're done. All right. I'll set you loose on this. Let me know when you're done. So Alexander, 100%. Okay. Technically, we've discussed everything in these checkpoints. So, I mean, we really would like to see perfect, but it's okay if you're not. If you're not, then maybe there's just a little bit more understanding that has to be given, or we can have more discussion around why. But we've discussed these at varying degrees. So some of them might be, some of these might be worded strangely. So Dom had another kind of follow up, which I think kind of is kind of on the heels of what I was just about to say. Are these representative of what you would see on the exam? I think the quality is lesser. Okay. When they do exam questions, I mean, obviously, they have to be very, very critical about every single word that they use. Make sure there's no room for poor interpretation, or, of course, also even like translation to other languages. There's a lot of factors. So these questions are written, I think, a little bit more haphazardly, right? So some of them are a little bit questionable, just in the way that they're worded. You kind of have to interpret it a bit. So in that sense, I would say no, they're not representative. In fact, like the way that things are worded and stuff might be a little bit, I think, a little bit clearer on the exam. Knowledge of some of the tools, like take the one where what tool can they use to visualize the correlation matrix. It's rare you're going to see a question like that where it's specifically just asking you what tool to use, but knowledge of that tool to use would still probably be important, because it'll still probably be in some sort of answer, but it may just be embedded in the answer. So what I mean by that is it might be something like, use Seaborn to do X, Y, and Z, and the X, Y, and Z are relevant to the answer as well, whereas Seaborn is a portion of it, right? So, or maybe they don't even directly ask you at all, and it's just kind of base knowledge you might have to know to be able to answer the question, right? So, are they representative? Partially, 2/3 maybe. There's definitely room for differences there between these questions and what you'll see on the exam. But the exam are multiple choice or multiple select. So in that regard, the format is very similar. Multiple select would be like choose 2 out of these 5, multiple choice, A, B, C, D, that kind of thing. They're similar questions, but maybe not exact. So again, if you're done, go ahead and use that green check to let me know you're done. Just to kind of see how many people actually got through it. But we're going to go ahead and start talking about it here. Good. I'll give just a moment, maybe like 1 more minute. Just giving just finals. Just a couple people still kind of wrapping up. So when you're done, just mark that you're done if you would. Well, let's go ahead and go over these. So I wanted to show you, kind of walk through these. I didn't sit and do it. I was actually trying to fix a couple of technical issues on my system here still. Trying to close out as many apps as I can, but I went ahead and just quickly just clicked through it. So my example actually has a whole bunch of wrong answers because I just randomly selected some of them. Whoops. Where was I? It's this one. There we go. This one right here. Okay. So, but we can still look through the questions and answers regardless. So data scientist wants to visualize a correlation between their data sets. What tool can use to visualize a correlation matrix, right? Seaborn and Matplotlib, I believe, are the two, right? And then we've got the mode would be used here. Categorical features, you want to determine which categories of particular features are most common. Be just the mode, and again, that's just knowing the differences here. Okay, there's not a lot of explanation needed for that one. A couple of them I just clicked on quickly if I knew the answer, but otherwise I just kind of, or if I just could click fast enough. But so as far as inverse or negative correlation, it still means that they're really close to being the same value, just inverses of each other. So we know if one goes up by 1 and the other one goes down by 1, they mean the same thing, just inverses of each other. We want to remove one of the features. So whether it's inverse correlation or direct correlation, it has the same negative impact on our model. So we need to pick one of the features. So we have to remove one of them. Okay. And then we've got, let's see, you're in charge of pre-processing the
Can I
data.
ask a question, please?
Yeah, go for it. Yeah.
So if you're going to remove one of the features, is there kind of an art or a science to choosing one, or you just drop one and then kind of move on?
Good question. You could experiment. If you only have a couple of features that this is a problem with, you could just experiment. Just try one and try the other, make 2 different models and, and see what the impact might be. You could probably try and theorize. At some degree, it could just be a trial and error, but also there are algorithms, as somebody brought up, like PCA is dimensionality reduction. So the idea of the PCA algorithm is you can actually make a model against your data to help you remove one of the features. So if you're not sure, you may actually take an extra step in your exercise and actually use machine learning to help you make that decision. But yeah, there is kind of an art to it as well. I mean, if you don't go that far and you just want to kind of pick one, I think part of it might be dependent on which one maybe is more representative of the business or really closer to what the problem is you're trying to solve, right? So I think I use the example of like sales versus revenue. We know that as sales goes up, revenue will go up. Doesn't mean our profits go up, but that would be a different discussion. If we're talking net or something that's different, but sales versus revenue, those are usually 2 columns that are going to be highly correlated. One of them's probably got to go. So then I would kind of think about the problem at hand, whatever it is I'm trying to solve, and which one I might think would have the bigger influence on whatever it is I'm trying to care about. So, if we're running a business, a retail business, and we want to see our busiest days, predicting our busiest days, do you want to predict that based on the number of sales or based on revenue for the day? That might make a difference, right? So, number of sales, maybe I don't really care if I have a whole bunch of little itty bitty sales. Maybe I'm looking for the biggest revenue days, so there's a little bit of an art to that. It's not always just a science. So I think in some of those cases, it's a little bit more of kind of stepping back and understanding the problem. And that's kind of a simpler discussion. The example I just gave you is kind of a simpler example. There's obviously some that can become a lot more complex than that, but yeah, there's no direct answer here, but one of the features has to go. So,
okay, thank you.
Absolutely. So, and by the way, if you don't remove one of the features, all you're doing is creating probably some bias. I mean, you're gonna cause an issue here in that you have 2 values that are going to kind of reinforce each other, if that makes sense, right? From your algorithm perspective, now you have 2 values that kind of both mean the same thing and could reinforce each other or even cancel each other out potentially if you got like the negative correlation kind of thing. So we don't want that. You got to think about it from algebraic kind of mathematical kind of point of view. We're just adding unnecessarily some other thing. If I have 10 apples in front of me and 8 are blue, and it's blue, 8 are green. I don't know what I was thinking. 8 are green and 2 are red. I could say have one value that tells me how many green and another value that tells me how many red. Is that going to help me? I know that if I'm going to stay with 10, no matter what, and they have to be either red or green, I know that as the green count goes up, the red count goes down, and vice versa, right? It doesn't do us any good to have a count for both if we know there's a total of 10 apples and all we're trying to do is predict how many green apples there are. Perhaps let's just count the green and let's forget about how many red there are. Just most basic of examples. Mathematically, you don't need that extra number, and that extra number can actually hold its own weight and cause its own issues by having that extra, right? So we have to kind of pick one that makes the most sense to what we're trying to do. Okay, all right. You're in charge of pre-processing. Did I do this? Oh yeah, remove one of the features. Okay, so pre-processing the data. You're publishing once to use for a new ML model they're building, which aims to predict the influence of an academic journal that will have in its field. Okay, so publishing company, what kind of data is this? I think this is kind of a vague I think it's kind of an awful question, to be honest. Just the way it's worded, I don't like this one at all. But basically, they're just simply saying what issues with the data might you encounter. I think what they're getting at here in the initial statement, the way I read this is just my interpretation, is we're talking about a publishing company, right? And we're talking about predicting the influence of an academic journal. So what are some of the things that the influence would require, right? Well, a couple of things. I'm probably going to have some plain text commentary kind of thing. I need to understand, do I even know who it's influenced or who it hasn't influenced? Do I have that information? There may be lacking information there. So missing values could be a problem. Outliers could play a problem. As far as overfitting and residuals and sufficient batch size, we don't know that information. And based on what this comment is, I think the main thing here is what can you confidently say could be an issue of outliers and missing values, but the rest of it I don't know, because overfitting and stuff, that all has to do with how I handle the data, a little less about the data itself that I'm provided. Maybe, I don't know. I mean, I think let's just move on. If you got this one wrong, I'm just going to give you a pass. I say, you know what? I think this is not a great question. And I don't think you're going to see a question like this poorly written on the exam. Okay, so let's move along. A machine learning engineer is creating and preparing data for a linear regression model. Okay, so we are predicting what? We're predicting numbers, right? However, while preparing the data engineer notices that about 20% of the numerical data contains missing values in the same 2 columns. So we have 2 columns that are problematic, 2 columns that are missing 20%. Now, here's another problem I see with this question. I'm just going to start off with a problem, the interpretation of this question. I see this as not clear enough. When the very first time I ever saw this question, I thought, okay, there are 2 different columns. Do we know if the information that's missing is in the same is together? Okay, so what I mean by that is it possible that if we have record one is missing data out of column 1, while record 2 is missing data out of column 2? Well, if that's possible, then in all reality, we could be talking about 40% of the overall rows are missing some value. Right? Think about that for a second. If it's 20% in column 1 that's missing, and 20% in column 2, and it's not the same 20%, you see how this could be interpreted in various ways. Another way to interpret this is that it's the same values. So if the data in column 1 is missing, the data in column 2 is also missing. That would just mean it's 20% of the data. So I don't know. I mean, this isn't clear enough to me as to which scenario we're actually talking about. But what they're trying to get across to us is that this is a substantial amount of data for these rows that is a problem. It's at least a fifth, but it could be closer to 40% of our data could be missing in some of the rows, right? So it's a lot of data that's missing. If we just remove those rows, if we simply remove those rows, we could be having some problems there. So the answer is actually to input the missing values using regression. So this would be take a mathematical algorithm against it. We're not talking about regression in the sense of machine learning and all of that. I mean, but literally just using regression algorithms, regression mathematics to input some values there, or just use the mean of the column. Okay, but by removing, the reason this one's wrong is what they're trying to get across is there's too much data here that we're going to lose if we remove actually this one says remove the columns. Sorry, if we remove the columns for that, we're gonna lose the rest of the column data, right? So that's not good. They actually changed this question on me. That's actually why remove the rows is also wrong though, right? So remove the columns. That's way too much data. We're going to also lose. Removing the rows, we're going to lose 20 to 40% of our data by removing the rows. Okay, so regardless of how you read it, 20 to 40% of our data is lost that we can't train against. And don't forget, there are 4 columns here. Only 2 of them have problems. So we're going to lose 20 to 40% of the other columns in the process. And again, we talked about this one the other day, where sometimes removing has a bias to it as well, and can tweak our data, skew our data because we're removing good values in the process, right? So removing the rows and removing the columns are kind of off the table because of the amount we're talking about. If we were talking about 1% or something, I'd say just remove the rows. But we're not. We're talking about a substantial amount here.
Brian,
And
quick
so
question.
the 2 options there would be input or fill the missing values of the mean, or using regression, one of the 2. Yeah, go ahead.
Yeah, so let's say instead of 20%, they said 1%.
Yeah.
Would literally, like, do you think the answers would change in terms of, like, it would be instead of select 2, it would be select 3, because if it was such a small thing, then you could remove the rows? Or
Possibly.
do you think it would be like one of those things that would still be select 2, but kind of similar to like
Yeah.
the SAT, where it's like select the best answer? Even if
Yeah.
there's theoretical, is that more likely what would happen if they brought that number down?
Probably. I think you're probably right. You're probably onto something. I don't know if the answer would change if they said 1%, simply because removing the rows carries with it its own challenge. You are removing good data, right? And so as far as the quote unquote best, and by the way, Amazon does have a lot of those kind of questions, especially on the architecture tests. What's the best? So if you can keep the good data and just fill in the missing values so that your algorithm doesn't crash, that might be better. So the question is then which strategy you use to fill it in. But I think, just in realistic, like real life kind of stuff, I'd probably say 1%. We may not even need to bother with the extra work and just remove the rows. But you do have to consider those rows could still have some very valuable information in them, even if it's a very small amount. Maybe they're outliers. Maybe there are a couple outliers, and those outliers add richness to our data that we're now losing if we strip them, right? So it always is kind of considered a little bit of a negative to remove the rows in general, because you are deleting good data in the process. So yeah, I would say it's possible they might just say select 2 of the best, and then they would probably be the same 2 answers, most likely. Yeah, definitely good thought process on that. So as far as the exam goes, you're probably not going to find something quite so vague. Like I said, the exam scrutiny, when they're creating the exam questions, it goes through a lot, and it goes through a lot of eyes and a lot of people that are supposed to tear it apart. And you're not going to typically see a question quite like this. It'll be a little cleaner in the statement initially, so there's no ambiguity. And there still might be a best. There might be some options here that would work, but may fall short. But if that's the case, they probably also would add some kind of a statement in the question, something along, not just add the missing values, but they'd probably say something like, how can the engineer add the missing values and maintain, a high level of of data or something. I don't know. I mean, you know, you get what I'm saying. They would probably add some sort of other criteria to the question that would give you some sort of a business objective so that you can understand that that wouldn't really be a valid business objective or something. You know, it wouldn't really fit the business requirements as much. So they would probably do some sort of other qualifier there. Great questions. And like I said, these are not as good of questions as you would see on the actual exam. So just, it's good if you can answer them though, because you know, get the wheels turning, get the thought juices going. But if some of your problems are what I've brought up, you know, don't worry, those are probably not issues that, you know, are you going to see on the exam. It's more about just, are you understanding what's going on here, right? What are they really getting at? Whether you got it right or wrong, is this stuff making sense? And do you understand it? I think you're doing good then. So again, a correlation matrix as well. This is, you know, basically just testing your knowledge on what a negative correlation means, right? Pretty straightforward. If it's negative, it means that as one goes up, one goes down. Okay. If it's positive, if it was a positive 0.95, then it would mean as one goes up, the other goes up. Okay. If you simply know that, you'll be able to answer this question. All right. Let's see here. Okay. And then this one's asking more about like SageMaker, and you will expect to see stuff like this as well. So I do want to point out, it's an ML exam on AWS. They're going to expect you to have some knowledge about AWS technologies, namely SageMaker will come up. So understanding the SageMaker architecture, understanding how these container kind of models work and what your capabilities are there is important so that you can kind of pull these things in. So this one saying that using custom XGBoost model. Okay, XGBoost is a built-in algorithm for SageMaker, but they're specifically saying this is a custom one. The company wants to improve its ML pipeline by porting its training and inference code, which they've written in R. So they've written it elsewhere, and they just want to use the same code they've always been using. And this is what's really cool about SageMaker, is all the stuff we've been talking about. If you got code already, that you can just drop it into SageMaker and start using it, right? There's ever so slightly minimal changes. And what we're talking about minimal changes, like a couple of lines, that'll have to be your inputs and outputs of the container. It'll be basically using the hooks that SageMaker has to use for those inputs and outputs. And the documentation walks you through exactly doing that. It would take you like 5 minutes to take existing code, put it in its own container, and load it into ECR if you really know what you're doing. Okay, it'd be really quick. It's just a couple of lines of code that would have to be added, and then you'd containerize it, put it out on ECR, and you could use it. So so that's where they're saying, look, the built-in algorithms, that won't work because we're talking to custom stuff. We're talking about using code that you've already written. It's written in R. It's special custom stuff. Okay, it's using really XGBoost is a standard built-in algorithm, and it's probably still just XGBoost at the end of the day. But it's the custom code that kind of goes along with it that we want to leverage, and the built-in algorithm isn't going to contain that, right? So there is no pre-built R container option. And then porting your existing code over to the container, that whole functionality doesn't exist. So there's a couple of things that actually make this question or this answer right here wrong. If you didn't know that there wasn't a pre-built R container option, if you didn't know that, you'll be okay, because you can keep reading and go port the existing code over to the container. You ultimately would have to build your own container to do this, okay? Which ultimately automatically takes you down to the answer. This kind of functionality, this is not the way it works. All right. The register the container in ECR. Yeah. If you have your own custom container, right, which isn't what they're showing you here. That's what they're talking about down here. Okay. So this one kind of breaks as soon as you start reading through, you start realizing, well, this isn't quite what, this isn't quite how it works. Okay. So you can create a new Docker container with the existing code, register the container in ECR, run the training and inference jobs using the container. All right. Notebook instances have really nothing to do with this stuff. I mean, again, that's just for the experimentation, but it has nothing to do with how the training process works, because the training does not happen on the notebook instance. The training happens in the training service. So this is just wrong in that sense. Okay. Again, knowing how the process works is important here. Okay. ML engineer. So this is a common one, right? We've talked about this one. Getting 99% accuracy on the data set when it's deployed into production, it performs significantly worse. If we see this, we're almost we could very easily assume it's probably some sort of split or randomization issue or something happened with the data. If our tests, our test data generates really high accuracy, and then production sees something, you know, crazy low, and there's a huge disparity. I mean, you're never going to get exactly the same. You know, production data is now and current. Training data may have happened a month ago, and could something have changed in that last month? Possibly, and that would kind of, you know, skew some things. But it's probably not going to be enormously large. Okay, so if there's a really big difference between your test and production, it's almost always a sign that you probably tested on the wrong data. You probably tested on the same data you trained on, or at least some of it, or something like that. So this is a very clear sign that that's what's going on. As far as scale the data, I mean, I don't even know what that's supposed to mean. I guess they mean scaling, like we're going to talk about scaling actually a little later on, scales and things like that. That won't have a factor on the difference between test and production. It may mean you just don't, overall, the model may not perform as well, and your tests would reflect that the same as production would reflect that. Okay. So if you didn't scale it, it may not perform that well, but your test wouldn't show 99% accuracy. Then your test would reflect what production would reflect. Okay. And then algorithm, using the wrong algorithm. Again, if it's not an optimal algorithm, your tests and tests in production shouldn't vary a whole lot. You would still have the same poor results. Okay. And then deploying the model. Well, is it working? Is it inferring things or not? Right. If it's inferring stuff, it's deployed, and there's not really, this has nothing to do with the quality of the predictions. Okay. Classification problem. What does the loss function measure? Loss function measures how accurate your prediction is with respect to the true values. Okay, this is what we were talking about before. Okay, where we're just kind of talking about, hey, we know the true values. How close to correct are we? And that's its kind of main thing that it's measuring. It's measuring the errors on how many times, you know, it got it wrong, basically, right? When we go into these others, loss function measures the steps you need to take to reach the optimal point. No, it doesn't measure anything. Okay, a loss function does not measure anything. It is a setting on how to obtain the minima errors. Okay, and the loss function calculates the iterations that you will take to reach your goal. It doesn't know how many iterations. It can't calculate that. That's not something it can do, because it doesn't know what it's going to see as it continues to go through. So it's trying to find that curve, but it doesn't know the curve in advance. It has no clue how many iterations it's going to need to get the best answer. It doesn't know that in advance. There's no way. Okay. So it can't tell the future, and there's no calculation here to know that. So that's not even possible. And then the last one here, loss function calculates the gradients of the weights for a particular iteration. Okay, a couple of things problem with this, words matter. It doesn't calculate, it does calculate the gradient, I guess you could say. It's understanding the curvature, if you will, but it's not a particular iteration per se. Okay, it's the curvature there is about the error rates that you're receiving, trying to find the least error on the weight that it's applying, right? So find the weight value that has the least error associated with it. Okay. So it is kind of calculating the gradient to some degree, but it's saying the gradients of the weights, right? Is it calculating the gradients of the weights, or is it calculating the gradients of the error? This is the kind of stuff you will see on the exam. Okay, it's paying attention to words. Okay, words matter, specifics matter. I mean, this is a very scientific thing, right? So we say calculate the gradients of the weights. It's calculating the gradient of the error. Okay, so this word right here negates this whole answer. Okay, so That's where measures how accurate. So it's a measurement. Okay, it's a measurement. The loss function. I do want to point out too, the gradient there, the loss function doesn't really calculate the gradient. The gradient descent that we're using in the loss function does. The goal of the loss function is to simply find the lowest error rate. That's the goal of the loss function. All right. Now there's different toolings or different ways to apply that loss function. And that's where like gradient descent, stochastic gradient descent, mini batch gradient descent, those are methods we can use to work with the gradient of the loss function, if that makes sense. Okay, so there's a couple of things here that, the word calculate is wrong. The gradients of the weights is wrong. There's a couple of things wrong with this last one. So it measures, the loss function measures how accurate a prediction is with respect to true values. It's just measurement. The question is, as we're making changes to those weights, understanding when the actual minima is and how often those measurements need to take place and stuff, right? Okay. Gradient descent is an important optimization method. Which one of the following is true about the gradient descent method? So select 3 here. It can involve multiple iterations. Okay, so like just regular old gradient descent, it'll go through the entire data set, and then it'll adjust the weight, go through the entire data set again. Okay. It says right here, uses a batch of training data points to calculate its next step. No. If we are doing mini batch gradient descent, it's not using a batch to calculate its next step. It's just measuring again, right? So gradient descent does a mini batch. If you choose mini batch gradient descent, it's going to be a batch of data, a batch of rows. It's going to go through those rows, and then it's going to adjust the weight, and it's going to go through the next batch of rows and adjust the weight and go through the next batch of rows. But it's not calculating its next step per se. Okay. It's not calculating that in that regard. Okay. It's more computationally efficient to use for large data sets. If you remember, like this just says regular gradient descent. So gradient descent, by the way, this number 2 also is implying mini batch. I'm assuming gradient descent itself does not. Okay, so specifics matter too. This does say just gradient descent. So that also makes this one wrong. And then in the computationally efficient for large data sets, if you remember, gradient descent actually breaks down with large data sets, right? The data set has to be able to fit in memory. So too large of a data set and it'll completely crash on us. Okay. And then we do know gradient descent does use a learning rate to multiply the effects of gradients. So there is a separate learning rate value that we're going to use to kind of understand, to work with those gradients, but it does apply gradient descent on top of that, right, to understand the gradients and whatnot. And then it tries to find the minimum of a loss function. Okay, so yeah. All right. Okay, anyhow, good enough. Hopefully, some of this stuff is kind of making sense. There's a lot to take in here, especially if you are new. Some of you have been working with this stuff for a long time, and it's been kind of on and off review, meets a little bit of SageMaker stuff and things like that. But others are learning this stuff kind of relatively from scratch. So depending on where you sit in here, obviously you're going to have harder or easier times with some of this. Okay, we're going to get into model evaluation, and then we're going to get you into your lab for the day. Okay, so model evaluation, we're moving along in our pipeline here, right? Let's just kind of jump through here. So model evaluation, again, don't forget, validation is going to help us identify where the model needs improvement. Now, we don't really use this validation set directly. It's indirect, where, again, the training process is using this as it's going through to know what true is. So it's going to train against the data that it sees. It's going to perform its calculations. And then every so often throughout the training process, it's going to validate what it's doing to kind of test itself, right? It's kind of a quiz along the way before the final test, right? The quiz along the way, make sure we're on the right track, make sure this thing is going in the right direction, kind of a thing, right? And then the test sets used at the very end after the model's done. And then we're going to evaluate the predictive quality by taking this data, feeding it through the system. We already know the answers, but we're going to strip the answers off, and it's going to predict. And then we're going to compare the known answers to predicted. Okay. So we talked about randomizing our data, avoiding overfitting and underfitting. So again, overfitting, it's you know, it's going to have a lot of bias. Underfitting, we're kind of just you know, kind of just on this flat plane here. We're not going to be very good there either. So we need to kind of find a spot in the middle, right? So this is where there's this concept of the bias variance trade-off. And we'll kind of explain what bias and variance are to help you understand these things. This analogy with the targets is something I've seen everywhere. Okay, it's I don't think it's unique to AWS trainings. Everybody uses this analogy. It's perfect. I mean, you see it on tons of blogs. You see it all over the place out there, on data science blogs and machine learning blogs and stuff. The best place to be is with low bias, low variance. Low bias, low variance. Bias is like adjustments on a site. Okay, so you know, if I have like a bow and arrow and there's these sights on it, and I'm adjusted, what would that be? Too low. As I put that on the target, every single time I'm going to be high. Okay, so every single time we shoot that arrow, it's going to be high. But I might have a really good quality bow, really good quality arrows, and this stuff just flies nice and straight. And so I'm off, but I'm consistently off, right? Is that good? Is that bad? It's up for debate. But I'm not going to hit the target, right? I'm always off here. And this is kind of a weird scenario, right? Because this could mean the difference between completely missing and getting it right all the time, right? So I'm not scattered all over the place. So I have low variance. The variance is kind of the disbursement of it or the grouping of it, right? And then the bias is whether you're on target or not, right? Bias is I've introduced my own bent, if you will, right? So the target would be assuming we're perfect and reality is reflected here, right? Bias would mean, oh, I've introduced something to it that is going to make all my predictions off by a certain amount, probably, right? I'm going to be predicting in a certain direction, and I'm going to be wrong a lot. And then you have low bias and high variance, like something like that. If I had to choose between the two of these, I'm thinking a lot of the times I'd probably rather have low bias and high variance, because at least I know I'm going to be hitting the target every so often. I'm not going to be wrong all the time. You know, imagine if this was a really fine target. Imagine if this was like a Coke can or something, and it's 50 yards away. You know, it's a soda can or something. This high bias one, I miss it every single time, 100% of the time. Doesn't matter how precise I am, I'm missing it every single time. At least with high variance, I'm gonna hit it every so often, right? So that's kind of the way I see this. And then if you have high bias, high variance, oh my gosh, that's really bad. Okay, now we're all over the place and we're way off. You're never gonna hit the target. Okay, so this is where there's always a trade-off. There's almost always a trade-off. To achieve low bias and low variance is a near impossible task. I'm not going to say it is impossible, but there's almost always a trade-off here. Usually, if we go low bias, as our bias goes down, our variance usually goes up. Okay, this is the classic, we call it the bias variance trade-off. Okay, if our variance goes down, a lot of times our bias goes up. Okay, so we would love to see them both go down, and under some conditions we can get it close-ish, you know, but probably not where every single one of them's in the red, you know, on the bullseye. Okay, so this is just kind of I like this analogy with the scattering and the kind of the showing you the aim and the target. So this kind of helps you understand the idea. Bias is the gap between predicted and actual. Low variance is how it's dispersed. There might be a certain amount of gap, but the gap is kind of around it, you know? So bias versus variance. Okay, high variance usually results in overfitting. High bias usually represents underfitting. Low bias, low variance is nice and balanced. Okay, that's what we want to aim for, but a lot of times it's hard to achieve. Okay. Okay, so I'm going to talk about both of these kind of higher level categories of classification problems and regression problems. Here's the thing. For the purposes of this class and the purposes of this exam, I'm really going to focus the discussion over here. When we get to this one, I'm going to kind of keep it high level. Okay. We don't need to go crazy over there. It's mathematical. It's a bunch of mathematical stuff that really is beyond the scope of the exam. And just like we showed you a bunch of algorithms before, right? A bunch of equations, I should say. I can show you the equation, but we don't need to go through it, and we don't even need you to memorize it. So for the sake of the exam, or even the sake of using SageMaker, all we really need to know is what these things mean, what they do. Okay, we don't really need to know the calculations. Since regression problems are all about calculations, I'm only going to go so shallow or so deep here. It's going to be pretty shallow because we just need to know, what is mean squared error, what is R squared, and you can do more research on this if you want at the end of the day. But these are probably much more relevant to the exam as far as really understanding the differences between these different metrics. Now, these are metrics around what we measure and consider success. Question around here, just on the chat, which is worse, underfitting or overfitting? That's a big debate. There is no direct answer there, Odette. But if you say overfitting is high variance and underfitting is high bias, look back here. If we have high bias and low variance, right there, high bias, low variance, right? This one I circled. Yeah, high bias, low variance. We're right here. That's underfitting. Okay. High bias, low variance. Like I said, it kind of depends on the scenario, depends on the situation and what it is you're predicting and how much this impacts you. I would say from case to case, it varies. There's no right or wrong answer here. There's no one answer to say overfitting or underfitting is better or worse, because it just depends on the problem you're trying to solve. But like I said, if I have high bias, but I'm really precise and I have really low variance, I'm going to miss the target every single time. If I use the analogy of that bow and arrow and a really tiny target, it doesn't matter that I have small distribution of the shots. It's the fact that I'm off 100% of the time. That could be really bad, and that could be terrible, right? So in that regard, I would say underfitting is really bad. Overfitting is typically kind of more over here. That's overfitting. Carries with it its own issues, right? But like I was saying, overfitting a lot of times, at least you're going to get on the mark once in a while. Okay. So if I have to trade off between these, I would argue overfitting is probably better than underfitting. But again, that's a very, very subjective, controversial kind of discussion in the machine learning space. As long as we kind of understand what the impact of these things are, it'll help us make those decisions, because then we can apply that knowledge to the scenario and go, well, gosh, if I'm off 100% of the time, what does off mean? If every single time I'm trying to predict fraud, I'm not predicting it because I have high bias and low variance, then I'm not even achieving my goal, right? But if being off a little bit consistently, on the same token, what if this is something like a mathematical prediction, like I'm trying to predict some number and I'm always over by just a little bit, or I'm always under by just a little bit. How much of an impact does that have on me? I'm still pretty accurate, relatively speaking, just off by the same amount every time. So, in that regard, maybe it's not as much of an issue, depending on, again, what that number represents. So I'd say it's scenario by scenario. Okay, there's no one answer there. And if you look on blogs and stuff about this, there's a big swath of people thinking in both directions. It's because it depends on the scenario. Okay, let's talk about classification problem metrics. Okay, so first off, what we're about to talk about, metrics. Okay, what are these metrics? These are measurements of our success. How good are we? Are we accurate? Okay, in fact, this is where we finally get to talk about accuracy. Okay, I've been saying all along that the word accuracy is a very kind of coveted word here because it means something very specific. And we got to be very careful using the word accuracy when we're talking machine learning. I haven't been overly careful using it. In fact, I've used it in the generic sense up till now because we haven't defined it. So I kind of could be comfortable doing that. But when you're talking to people around machine learning, be very, very careful with your words here. And if you're talking the word accuracy, but you actually mean precision, you're going to cause issues. Okay. Words matter. Language matters, right? So be very careful with your words when we're talking around these things. Specifically, the word accuracy sneaks out with a lot of people's vernacular, and we got to be careful with that. Okay. Use precision when it's precision. Use recall when it's recall. Okay. So here's kind of an example of what we're looking at, right? True values and our predictions. So the green are the times that we were correct. Okay. We predicted it was a cat. It was a cat. We predicted it was a cat. It was a cat. Predicted it was not a cat. It was not a cat. Okay. So you notice predictions, you can be right when it's not a cat and you can be right when it is a cat. The question is, are my true values and my predictions in alignment? Okay. The gray are when we were wrong. Now, what we see on the screen right here, I just want to point out, this is we're only correct 50% of the time here. This is pretty bad. Okay. We were only correct 50% of the time. Okay. So for classification problems, a confusion matrix is often used. We'll show you this, what we call confusion matrix. Now, don't forget, we have a correlation matrix and we have confusion matrix, two very different things. Correlation matrix helps me understand if features are correlated with one another. Okay. A confusion matrix is about measuring our predictive quality. Okay. And so we end up with this matrix of 4 values here. Okay. It looks just like this. It's 4 values. So P and positive and negative. Okay. So if our actual was positive, so it was a true. Okay. So like if it's a cat, it's a true. If it's not a cat, it's false. Okay. So yes, it's a cat, and we predicted it was a cat, then that would be a true positive. If we said, no, it's not a cat, and we predicted it was not a cat, okay, so it actually was not a cat, and we predicted it wasn't, we're also true, okay? So we want most of the stuff to kind of reside in this area, okay? Those are both correct statements, okay? Then we've got our false negatives and false positives. So false negative is we predicted that it was not a cat, but it was. Okay, it actually was a cat, but we said it wasn't. And we said that it wasn't a cat, but it was. I'm sorry. We predicted it was a cat, but it was not. Okay, yeah. Anyhow, all right, so you get the idea. So we want to have the true positive, true negatives. Those are good. The thing is, sometimes these values have different weights in terms of what we care about. Okay, what is the problem we're trying to solve and what's important to us? All right. So give you some examples. If we talked about fraud, right? If all we care about is accuracy, accuracy is going to be all of this divided by the I was gonna jump ahead. I'm gonna save that because we actually have a slide to show you this. So I don't want to jump ahead. I'm gonna table that for just a second. But basically, are we gonna use all of these values, or are there only particular values we actually care about? That's kind of the high level I should mention at the moment. Okay. So maybe I don't really care a whole lot if the actual is no, but we predict it's true. But what if it's true, and we predicted, no, that might mean a lot more. That might mean a lot more to me. So this false negative might actually be the most important factor to me. Or this true positive. Maybe I don't care about true negatives. I only care about true positives and false negatives, that kind of thing. So what's more important to us? And that's where these different measurements, these different metrics come into play. Okay, they mean different things. So again, we've already kind of walked through that. Okay. So again, we have true positives and true negatives. These are correct predictions. And so accuracy is our true positive and true negative. So our trues, okay, divided by all. Right? Does that make sense? That's pretty simple calculation, right? Out of our total predictions, how many times were we correct? That's basically what this is telling us, right? So if we have lots of true negatives, this might not be overly effective. And again, like we were talking about with fraud, what if I'm 99% accurate because in reality, fraud only happens 1% of the time? I probably want to care more about some specific thing. I want to care more about, I want to make sure that if we're saying fraud is positive, okay, so if fraud, it's a positive, I want to make sure I care about the true positive and false negative. Those probably make more sense to me in that context, right? If I'm thinking that way through correctly. So, I want to make sure that I identify when it is fraud. I want to make sure we're clear on identifying that. And I also want to see when I said it wasn't fraud when it was. But maybe that's not the best either, because I also might have a situation where suddenly I'm predicting a bunch of things that are not fraud as fraud. And that measurement may not be ideal either. In fact, we'll talk about it in a minute here, but maybe F1's better for that scenario. We'll come back to it. Okay, so accuracy is just total times we were right divided by all. Okay, pretty straightforward. Precision is best when the cost, meaning the if we're wrong, it's going to hurt us really, really bad. Okay, the cost of false positives is high. Cost of a false positive. So it was not the case, and we predicted it was. And so put this into context. These types of discussions, where we're talking accuracy, precision, the next one is recall. So, think about scenarios, somebody predicting cancer. Okay. What is the cost of telling somebody they have cancer when they don't? And what is the cost of telling somebody they don't when they do? We have to weigh that out. Okay. There's a cost in either case, but which one's worse? And so, that again may be up for debate. I don't know. But I would argue, we would, if somebody does have cancer and we tell them they don't, and they're not getting treatment, that, depending on the cancer, that could kill them, right? Versus we tell them they do have cancer when they actually don't, it will depress them and hurt them mentally and emotionally and be a really big problem there, but it's not going to kill them most likely, right? So you have to kind of understand, weigh the importance of this, right? So again, accuracy is all trues divided by all. Precision is true positives divided by the true positive and false positive. So the total of just these. Okay. And then recall, which you'll also hear is sensitivity. Recall and sensitivity are the same thing. Okay. This one is going to be true positive divided by the true positive and false negative. So this is best when the cost of false negatives is high. Okay, false negatives. So we say, nope, you're clear when you actually have cancer, right? That could be a pretty high cost. Okay. So that's where, machine learning is being used in all areas today, right? And some are, the impact is greater than others, right? Medical things, there's literally life and death, at the hands of the model. Same thing with airlines, right? Flying airplanes that are using machine learning. But on the same token, if I've got a camera and it's taking pictures and it's identifying faces in the picture and it doesn't identify a face when it should, okay, right? Nobody's going to die because of it. So we need to understand that the importance of this stuff changes and how we're going to apply what we consider important changes. All right. And so it's never a black and white, just always look at this metric, always look at that metric. And same data. I could with the same data under one condition, I might care about one thing, and under another condition, care about something else. It all depends on the business requirements and whatever it is I'm trying to do here. Okay. All right. And then there's what we call an F1 score. And this helps us express precision and recall. So it's kind of a weighting between precision and recall as a hybrid score of the two of them. So F1 score gives us the best of both. What you'll notice here is recall or sensitivity uses these top two values. Precision uses these two values. Neither of them use true negatives. Neither of them. So you could also understand that an F1 score does not care about true negatives a whole lot. Okay, true negatives don't really matter. Okay, we're really putting an emphasis on true positives, but maybe a weighting between whether it's a false negative or false positive. Okay, so the F1 score is a hybrid between the two. All right. Then we also have what we call the AUC ROC score or curve. So area under the curve is a degree of separability. And then ROC is actually the probability curve itself. So kind of show you what this looks like, something like this, okay? So it uses sensitivity, which is the true positive rate, and specificity, which is your false positive rate. Okay, true positive and false positives are what we're looking at here. True positive, false positive, okay? And so that's how this is measured, right? So you can kind of see the scale here, or the measurements here, right? So the axes, false positive, true positive, okay? So we have this score that gets generated, and so we'll look stuff like this, right? We'll end up with these different scores. There's no one number that's right. We have to kind of play with this and understand where we're going to draw the line and what's important to us and what we're doing. So there's no direct answer here. But we kind of see how we maybe play with these different settings, different hyperparameters and different things about our model, and we have different scores that are going to come out, right? And then we can kind of find the one that's got the best score for what we're trying to do. Okay. And again, in this case, spam or not spam. So where do you want to land? Let's say we're developing a spam solution to catch spam. Again, where's the importance lie? So there is a risk. So let's talk about spam for just a second. We're saying we're going to call it spam. Okay. And if it's not spam, we're going to flag it as not spam. So let's say if it is spam, it goes in the spam folder. Okay. But if it's not spam and ends up in the spam folder, couldn't that be a pretty big deal? So what if, one of your chief executives, no, those are different, right? So, specificity. Sorry. I see what you're saying. Did they use a different word here? Sorry, just make sure that we're, the false positive rate. So the false positive rate would be, this one. Yeah, the precision. Yeah, good catch there. Good catch. I actually don't use the word specificity a whole lot, so that one kind of throws me for a loop too. But yeah, good question here. Oh, so I just got a private message sent to me. I guess somebody used a computer to buy a lottery ticket, They won, and their spam filter classified it as spam. Oh my gosh. Whew, right? So the cost of something being classified as spam can really hurt, right? So what I was getting at there, same exact idea, is imagine, one of your chief executives is making some big deal. It's a, it's $1 billion company deal, and they're waiting for some email back on the deal, and there's a window of time you have to close within, and emails are lost in spam, never to be seen, and then the window closes, and that's that, right? So, right. So sometimes the cost of calling something spam when it's not is really high. Meanwhile, if you get a little bit of spam in your email box, do you really care all that much? I mean, a little bit's okay, right? I'm gonna be okay with a little bit. If it means that almost nothing that's real gets into my spam box, right? I would rather have a little bit of spam to make sure I don't miss those important emails than to have important emails that end up in my spam box, right? So understanding, again, what's important to the scenario, okay? But on the same token, taking that idea of classifying it as not spam maybe is okay by me a little bit, right? But saying it's not cancer, well, that's a different discussion, isn't it? Right? Because what if I'm wrong and I say it's not cancer and it is, and we miss treatment opportunities and the person dies because of it, right? So we have to understand that. And that's where machine learning is a science, but a lot of science people, a lot of scientific people want black and white. When do I do this? When do I do that? I'm sorry, but I can't tell you that. And nobody can, nobody should be able to. If they do, I would doubt the person telling you, okay? If they tell you always use F1 scores, always use sensitivity, no, sorry. If they're telling you that, forget anything else they have to tell you, because they're forcing you down a path that is not wise. Okay. You need to apply this knowledge of understanding how and when to apply these things so that you can choose the right thing to measure as success from case to case. Okay. It's very, very important. So as far as your exam goes, I'm sorry to tell you this. These are not complicated calculations. I'm sorry to tell you this. You will need to know this. Okay. You will absolutely need to know that precision is your true positives divided by your true positive and false positive. You'll need to know that. Okay. And now, do you have to quote unquote memorize this formula? This isn't much of a formula, right? The way I do
this is the count of all true positives over the count of all true positives plus false positives, right?
Correct. So positives, right? It's about positives in this case. You notice negatives aren't even part of it. So the way I do this is I don't care about the calculation so much if you understand what it is you're doing and why you're doing it and how that maps to the word precision, right? So what are we doing here? We're just trying to specifically say, look, false positives are a really important factor to me. I really don't care about negatives in general. Okay. So with precision, the negatives, whether they're true or not, or whether they're false or not, doesn't really matter to me. Okay. Yeah. Positive. Precision. Yeah, exactly. Precision is the positives. Okay. Accuracy is all of it. I think that one's easy for everybody to grasp most of the time. Recall or sensitivity to understanding that we're really trying to say, look, we're still focusing on true positives, but we don't really care if it's a false positive all that much. But we do care if it's a false negative. Does that make sense? So just understanding what you're doing here will make it really easy for you to understand the calculation that's going to take place here, because you understand what it is you're doing. Right. Because the calculation is pretty darn simple when it comes down to the actual math of it. Right. But you will need to know these calculations. Okay. All right. Awesome. Good enough. Now I mentioned regression. We're going to be kind of quick on this. So regression is about math. Okay. Right. So again, you don't necessarily need to know the calculation itself. It's just good to know what the calculation does or means. Okay. So mean squared error, MSE, the main thing here is you're really just kind of taking the difference between the prediction and actual. You're squaring that difference and you're summing it all up. Now this is all built into the tooling. You can just say, I want to use MSE when you're talking like scikit-learn. So that's why, again, you don't need another calculation because you're not going to perform it. You don't need to actually perform this calculation. You just need to say, hey, scikit-learn, go use MSE, right? So again, that's going to come down to understanding what it is you're using. You know, why are we using it? What is it for? So really, it's just kind of the difference between the prediction and the actual. When it comes down to it, it's this delta, right, that we're looking at here. So we have our actual, we have our error, we have our predicted. Kind of what's, you know, how far off from that are we, basically, in a nutshell. Okay. And then you have R squared. Basically, it's another common metric. It's good with linear regression, and basically it's a fraction of the variance. Again, variance, right? Fraction of the variance accounted for by the model itself. Basically, this is going to report a number of 0 to 1. All right. So the reporting on this is 0 to 1. It's not either just 0 or 1. It's a range. Okay. It's a scale. So you could have, you know, 0.25, you know, or from 0 point something, all the way to 1. All right. When it's close to 1, it's usually a lot of variabilities in the data. Okay. A lot of variabilities in the data. But again, play with this. I would say, it's something I would say go do a little bit more research online, just kind of dig up information on R squared, and you'll probably find more, you know, cleaner information on understanding when it's a good time to use this. So this is just, you know, just again, it's about, you know, to keep in mind, this is all part of regression problems and identifying our predicted values and how accurate we are, right? That's what it comes down to. And then there's different measurements for that, with MSE being one and then R squared being another. And then there's an adjusted R squared as well. This basically just takes into account the effect of adding more variables. And so it, you know, increases these things. And so it's kind of going to be able to handle more of those. I would say just go do a little bit further digging. These slides don't really do you much justice. We could go pretty heavy into the math, which is kind of unnecessary here. Again, Amazon's not going to quiz you on the math. So it's one of the reasons why we don't get into it is the deep dive in the math doesn't really matter all that much. However, to help really understand these, you may want to get into the math, but not for the purposes of memorizing the math, for the purposes of understanding what's going on here. Because if you understand what's going on, it'll help you know when to use it, right? It all kind of is a full symbiotic circle there, right? So instead of somebody just saying, oh, under scenario X, Y, and Z, use R squared, it would be better to understand how R squared works and really what it's doing so that you have a better understanding of when to apply it. Okay, instead of just some, under these conditions, do this. Unknowingly why, just do it, right? I don't like learning that way. I don't know if any of you are in the same shoes. I prefer to know how things work. And then it helps me understand a lot better on when to use it, right? So, you know, take it for what it's worth. You're probably not going to get a whole lot of questions on these things on the exam, on the regression side of the house. Most of the exam is going to be more on the classification kind of side of the house, that, you know, that other stuff, precision, recall, ROC, or AUC, ROC, that kind of stuff. You're probably not going to see much here, but it's possible you could get a question or two on this. So it's good to still know, but I wouldn't spend hours on it. Okay. And then again, just a little bit more on this. So R2 will always increase when more variables are added to the model. All right. And again, our adjusted R squared, it's a better metric for multiple variance regression. So, you know, go do some more studying on this. If some of this stuff doesn't really make any sense to you, like I said, I wouldn't stress too much over these particular ones. But if you can spend some time to maybe watch a couple of YouTube videos on it or something, you'd probably be good to go, right? Just get a little better understanding of kind of when to apply it, how it works, you know, what it's doing. And there's probably some good stuff out there. I just don't have any resources for you on this one that I can share with you off the top of my head. But this isn't anything AWS specific. You could certainly, there's no shortage of this kind of information out there. Okay. So we're going to stop there. We're going to do lab 3. Okay. Let me explain what we have to do in lab 3. This is very different. Well, I don't say very different. It is different from yesterday. There's a couple of extra steps you're going to have to do. In fact, I'm going to edit this slide to fix a couple of the steps for you. In fact, give me just a second. Let me do that right now, just so there's no confusion. So what we're going to do is, okay. Sorry, give me 2 seconds here. I know 1 1000, 2 1000, right? Okay. Okay. So here is what we're going to actually do. I just changed the steps a little bit. So what you're going to do is you're going to log into SageMaker. I'm going to have you upload your project from yesterday. Okay. You upload your file, your project file from yesterday. Here's the thing. Go into that project file before you do anything else and edit the S3 bucket. You'll notice in the instructions it tells you to do this. The S3 bucket from yesterday is different than today. So the one in your code will not work. The one in your code that you saved from yesterday will not work. So update it with the new bucket that is going to be in Quick Labs for you today. Okay. Once you have edited that S3 bucket in your code, run all of the cells from top down until you get to the end of where you ended yesterday. Here's the reason why. All the variables, all the stuff in the code that you generated yesterday won't be there. So you can't just pick up right where you left off yesterday. You kind of got to get it all built again. So you're going to have it go through a training process, go through the data pre-processing phase. It's going to have to go through, all of those steps, and then you'll be ready to do some of the next steps, the actual training process you're going to do. So you're going to do the same thing tomorrow, by the way. So what it's going to do is going to establish anything it built yesterday. You're going to do it again. Now, I don't think there's a lot that you built yesterday per se. Most of it was data pre-processing, but you need to do that data pre-processing again. That's kind of the point. You need to make sure that your splitting has taken place, that your data is cleaned up and all the work's done on it so that you're ready for the next step. Okay. While that is running, you can go ahead and just leave it be, let it run. And go open the notebook for today's exercise. So there's the PE-training exercise. So while you're letting your project run, because those steps might take a little while, you don't need to wait for them. Just kick them off. Go back to your PE-training exercise, go through that exercise. When you're done with the exercise, then go back into your project and work on your project. Okay. And we're just doing the lab 3 project content today. So don't go into lab 4. So just like yesterday, you'll see a point in there where it'll tell you to stop. It'll say stop and save. All right. Same thing yesterday. Make sure you save off your work when you're done. Okay. Very important. So we're kind of late into the day. I'm guessing this might just take us through the end of the day, just kind of like yesterday. We'll have to kind of see how everybody's doing, but we're almost at 3 o'clock and class goes until 5 officially. But we'll kind of see how everybody's doing. We may stop and have a little bit more kind of self-study conversation, things like that. But we'll see how everybody's doing. I'm just going to check in periodically, but we'll check in probably at the hour mark, see how everybody's doing, make sure everybody has progressed into their project at that point. The exercise, if you want to give yourself a little more project time sooner, go through the exercise quickly. Okay. Again, the exercise is just to kind of illustrate and teach you some of the concepts, but you're going to apply them in your project. So since you don't have a lot of work that you actually have to do in the exercise, like for the most part, you're pretty much just executing the cells. You don't need to spend forever in your exercise. This is another place I see people fail is they'll spend an hour and a half on the exercise and they go, gosh, I just started with my project and we're already trying to wrap things up for the day. Well, it's because you took way too long on the exercise. Okay. The exercise is not intended to be something you sit and dissect for 2 hours. All right. It is intended to be a 30 to 40 minute exercise. All right. The training stuff is going to be some waiting periods. So as far as breaks go, for this day, your training is going to take some time. Okay. So use those when you're kicking off a training job. Those are good times to say, okay, I'm going to go take a quick break. Okay. So instead of taking a separate break and having nothing happening with your lab where you're kind of just wasting time at that point, you can kick off your training job, make sure it doesn't immediately error out. So make sure you got it right and it looks like it's going. Go take your break. Come back after 5-10 minutes, and it should be done. Okay, but that way you're kind of multitasking. Your training job is running while you're taking your break. So that's how I typically manage my time here, and that'll really make a big difference. And then same thing, you're doing your exercise. Your exercise is going to have a training period in there as well as your project. So both times you're going to actually have some breaks in there. So maybe you just take like a 5-minute break and then a little later take another 5-minute break when the next training job is going on. I don't know, something like that, but manage your time, however you want to do that. But ultimately we'll check in on you periodically. I'll check in like an hour and then like around the 4:30 time period, we'll kind of see how everybody's doing. And if you just need to keep on working, then that's fine, But I don't suspect anybody will be done by 4:30. So this will probably take us out to about that 5 o'clock mark. Okay. Everybody have a great lab 3. Let me know if you have any questions here. The lab should be all built and ready to go. As before, I am here for you. I'm not going away, but I will be quiet and on mute. So if you need my attention, just grab it in the chat. Okay. Have a good lab. Let me know if you have any questions. Don't forget, do the exercise before the project. However, load the project file first and run it, modify that S3 bucket, and then run the cells. Then switch back over to your exercise, do the exercise, come back to the project. Does that make sense? If you have any questions or confused about that, let me know. I can help you one by one. All right. The bucket name is in the code. You'll see it in your code. Just walk through your code and you'll see it in there. Or you could do a find. I think you probably do a search for it. But if you just do a search for like bucket, I think if you just do a search for bucket, you'll probably find it. But it should be towards the top of your code. It's not going to be very far in. I don't remember it being very far down. So just look through your project code. You'll see it in there. I don't know if anybody else can kind of help you. I could probably open it up, but you shouldn't have a hard time finding it. Just do a search for it or kind of look towards the top. Let me know if you can't find it. I'll try and find the exact string to search for. All right, everybody. Let me know if you have any questions. Just to recap on that one, as far as where you find your bucket. Every project is a little bit different, right? So there's 3 different projects. So like if I go into the reviews one here, I'm going to open up each one of these here. So if I just do a find, didn't seem to load well. Oh, go figure. I think I rushed it. All right, let's look at these others. So it's going to be down base path, data preprocessing. Did you do a bucket yesterday? Maybe this is just for tomorrow. I thought you had a bucket in here.
I think it's for tomorrow when I was doing a find all for the bucket, at least for the weather one, it was not mentioned until lab 4.
Okay. All right. So I'm mistaken, I think, on that one. Thanks for clarifying. I like this bucket right here. Don't change this because this is where the actual data is coming from, right? So that's okay because that's not your bucket. This TC large objects, this AWS-TC large objects is a bucket hosted by Amazon for the lab data. So that's fine. That's fine. Anytime you have outputs, though, any outputs, it's going to probably ask for an S3 bucket. But I don't think yesterday you did any outputs. You just worked with the data and left it local on the node. So yeah, you may not have a bucket name. Thanks for chiming in on that because yeah, I think it's probably just for tomorrow. Then we probably don't need to modify the bucket name today, but tomorrow you're probably going to need to do that. Right here, actually, was this? Okay, yep, right here, step 3. So this is after lab 2. So sure enough, so this one is the credit card fraud, and I'm sure all of them are probably in a similar boat where you're going to define a bucket name right here. And then so tomorrow you're going to have to put the new bucket name in there. Okay. So don't worry about changing a bucket name from yesterday. It looks like this is just going to be a task for today. So just run the cells that you did yesterday up until this end of lab 2. And then don't worry about anything else. Don't worry about changing any bucket names or anything. Just run your cells. Okay. So like I'll do this. I'll come in here where it says end of lab 2. I'll click on it. And if you come up to cell, you can say run all cells above. Run all above. It'll run all of the cells from the top down at the top of this line right here. So I like to select this and just say run all above, and then it'll run all of them for you. And then I'll move over to the project, or excuse me, I'm sorry, to the exercise, do the exercise, and then come back and do this. Okay. All righty. Hopefully that helps some clarification. My apologies for adding that extra layer of confusion. I will fix this slide as well. All right. Let me know if you need anything. Just a quick check in on everybody. Is everybody, maybe you can just go ahead and use the green check there. Let me know that you're actually working on your project and you've gotten past the original exercise and that you're doing okay. You're on track. I don't expect anybody to be done at this point. We are at about almost 4 o'clock. We're only about an hour in. So I figured most likely you're all still working. I don't expect anybody to be done. But we'll just want to make sure everybody's on track. Everybody's good. I think we'll just go ahead and just have you work on this lab for the rest of the day. I don't want to rush anybody, and officially our time goes until 5. So we'll just kind of let you just keep on working. As far as exam prep time tomorrow, I think I'll just take a little extra time because I think we'll have some more flexibility tomorrow. So instead of the half hour today, we'll kind of just tack that on to tomorrow. We'll do a bunch more extra stuff tomorrow on when it comes to exam prep time and letting you have some time to review. We should be able to end a little bit early tomorrow, so that you can take that time to do some self studies, do some sample exams, and things like that. Whatever you'd like to do. But today we'll just go ahead and let this just run on through, and I don't think we're going to do anything else. So don't expect to have to do any other discussion time or check in or anything. So just go ahead and work until you're done, and then when you're done, you can just go ahead and leave for the day because I suspect a lot of you will need all the way up until that 5 o'clock time period. So I don't want to rush anybody. Some people might even want to go longer than that. So it's up to you. All right, but we're gonna say discussion for the day is done, and we will see you tomorrow. I'm not going anywhere. I'm still going to be here until 5. But in the meantime, if you need me, just let me know. Just check in. But otherwise, whenever you're done, just go ahead and move on, and we'll see you tomorrow. Okay, everybody. Again, if you need me, just let me know. I'm here. I'm not going anywhere. All right, everybody, have a great night. So if you do decide to leave, that's perfectly fine. You don't need to ask for permissions or anything like that. So just go ahead and whenever you get to that point, be good to go. All right. We'll see everybody tomorrow. For anybody that's still hanging out here, I'll mention this in the morning as well. It looks like I got a note. Looks like from Anna that specifically on the credit card fraud project, there's a spot that we get an error. Let me just kind of restate this one here. It's specifically when you're running the predict batches command. I guess there's an error, and even the solution file that's provided, the error exists, but the code back from the exercise works. So we'll want to do some sort of comparison to figure out which one of those, why the exercise code works and the solution file does not. But if you're doing the credit card fraud project and you've got an error there, or you're coming up on that step on the batch, on the batch work there, just make sure that you go check out the code from the exercise, and that might help you out. Okay, so again, this is for the predict batches command, actually, specifically. So I guess it's because, according to Anna here, the error was during the split that lists types that don't have an attribute label, and you get an error for it. So the split code from the exercise worked okay though. All right, so a little workaround there, a little just kind of see that there's a fix for that, if you will. But ultimately, we'll talk about this tomorrow too when everybody else is here, since there's only a bunch of people have already left. So anyways, I just wanted to bring that up, and then we can talk about it tomorrow too. Okay, all righty. Just wanted to mention that. Okay, keep on working if you're working. Whenever you're done, go ahead and leave. We'll see everybody tomorrow. I'm going to stick around for another 5 or so minutes, then I'll end the Zoom session. But you can keep on working as long as you'd like. Okay, no one's going to cut you off. We'll see you tomorrow. All right, everybody, take care.